Welcome to APEC. It's August 30th, 2025, and I'm your moderator, Tim Ventura. Thank you to everyone for joining us on today's call, along with everybody who was watching us on YouTube. So, today we are going to be doing a special tribute to Dr. James Woodward, who passed just a couple of weeks ago. And so that is a large and unexpected event. We're trying to get everybody organized for that. I was going to start with that, but now it looks like we will wait a bit as people kind of trickle in there to speak about him and share their thoughts and memories and all the wonderful things about his legacy. We will absolutely and dearly miss him. So we're going to start with Eric Reiter, who is going to be talking about matter waves are not probability waves. Eric has a really in-depth presentation. It's really amazing. He's been putting this thing together all month. I am so excited to be able to share this with you guys. Then we will be doing a tribute to Dr. James Woodward. And after that, Jack Sarfatti is going to be walking us through some of his collaborative work with AI that's helped him develop a lot of mathematical formulas and what he has described as some breakthroughs using conventional physics that help his work with warp drives. So I want to thank everybody again for joining us. In terms of news items and updates, I guess the biggest thing, and I can show this later, is the Alt Propulsion website. I have been adding in select feature articles to that. So if you visit our website at altpropulsion.com, not only can you get conference replays and basically all sorts of information about our speakers and all of that, you will also get a list of key presentations along with detailed summaries that I have been putting together there. I've got about 80 of those loaded. I have many more to upload. The other thing that I've put in is I have done research and added details for every single one of our speakers. And again, that is, I think we're pushing over 100 different speakers there, and I have a few more that I think I have to add as well. So we have lots and lots and lots of information on the website at altpropulsion.com, and I'll be doing updates for that as well. And again, if you are following the UAP phenomena, we have another website that is worth mentioning. It's called UAPRev or UFORev.com. Check that out. That has the details about everything that is UAP related, and the propulsion stuff I'm trying to silo into alt propulsion. That just makes it easier for people to do research based on their key area of focus. So without any further ado, let me bring Mr. Eric Reiter in. Eric, thank you so much for joining me.
Very good. Thank you, Tim. So
Yeah.
I have an elaborate set of slides. It's very complicated. It's really best if you follow the mouse for the slides and hear me, and there are extra details to understand later. And
Okay.
it's all at the top of thresholdmodel.com. So
Eric, let me do this. What I'm going to do is, yeah, I'm sorry. I'm going to take myself out. I will be here if you need help. Again, you have an amazing setup on your end. You're able to switch audio. You have video you're going to be demonstrating. You have a complete walkthrough, and you have a pretty amazing physical model you're going to be explaining. So I'm going to disappear into the background and hand things over to you, sir.
Thank you, sir. So to really understand what I'm up to with this threshold model, I do a skit with cups to understand the experiment. In most cases, everything is thought to be quantized, as if it's a full cup or an empty cup, but you don't know where it is. There may be something partially loaded, but you won't see it. And that's what I'm about, to show that there's such a thing as a partially loaded state. And so you start with a full, and you go to two detectors, which could be of any amount, partially, possibly. And you throw it over here. You start with one, you throw it to the other two detectors, and now it's full, and it's a rule. I'm saying you only see when it's full, and then it all spills over. And then you get two. That's what the experiment is about. It's 2 for 1. And the way it connects to all the alt propulsion stuff is to understand that in the case of energy, the dark energy is this partially loaded state, and the dark matter is this partially loaded state. And I'm able to see it and show its identity and how it works with this 2-for-1 experiment. Now to the slides. So in this experiment, I'll explain it later, but what happened in history is that they started with seeing everything as particles with the electron and saw wave effects. And then also with diffracting helium by Esterman and Stern in 1930, and it fit the de Broglie equation. And so that was the beginning of the paradox. But it was explained with the probability interpretation by Max Born, but Schrodinger hated it. And all this quantum stuff, the greats argued against it, but somehow it was what we think is now. So, but it's difficult to even talk about this stuff. The words matter, and people have been describing their experiments in terms of photons. That's a big mistake, and you'll see how they do that. So please be careful. I'm saying to describe things in terms of the clicks and the experiment to tell what's going on in the face of this wave-particle duality and the photons and such. So this is one of the greatest sentences in physics to me because it explains the real wave-particle problem where it's impossible to visualize it as understood by Einstein. This is Einstein's model of the photon, that it has two parts, the particle part and a wave part. A particle, if you start with understanding that it's quantized, you'll have the idea and you'll even see it in experiments. But I'm saying the experiments were not done right, but they think it is right. And this is what they think they see. What they see is that it looks like it goes one way or another at a beam splitter. And there are these clicks that happen. But if you were to reconverge the beam, you get an interference pattern. That's the wave particle problem. Now, I'm going to be concentrating on this particle part. And the detectors make clicks. They make pulses, and we look at the time between the pulses and plot it on a time difference histogram. So if the times between the clicks are random, you get this band of noise, and we'll see more of that. And quantum mechanics predicts this. So when they see the noise, they think it's quantum mechanics, and that's what's happened in the past. I'm going to show you quickly the history of how they did this, how they saw these experiments. So back, what is this, 1946, they did a split with X-rays, but there were many problems. At least they got the math right, the chance equation, the rate in the first detector times the rate in the second detector times this time window. I'll explain that. And compared to the rate of coincidences in the experiment. So this ratio by quantum mechanics is expected to be 1, and that's what they see. So at least they know to do the split and to see this ratio, but there were still problems. Anyway, this is the next experiment. They had the chance equation right. They're comparing the same way, and this is the time difference histogram, and it's a band of noise. So here you could see it's a beam split coincidence experiment. They did this right, and that it's a beam split right, and the time difference histogram right, but still there were problems, and they don't have pulse height resolution, and I'll show more about that. The next experiment, here they have the time difference histogram, and it's this band of noise. This is a more elaborate argument where it starts with 2, and he has the coincidences between the 2, and he sees a peak, and he says, oh, therefore, this one side has to be 1 h nu, and then splits it. And then you see the band of noise, which makes it look like it went one way or the other at a beam splitter, and they say it's quantum mechanics. But there were all kinds of problems. They had no energy budget, no energy resolution. And of all nutty things, they used a polarized beam splitter which would route the light. A polarized light would start. It would route the light one way or another. And so there are all kinds of problems with the way they did these experiments that convinced everybody that it's photons. And then these next experiments by the French team, they had the same problem with the polarized beam splitter. But here they go a little further to say, oh, we're going to start with an emission that makes 2 and do a triple coincidence test. But they did not use the triple coincidence chance equation, which is well known in nuclear physics. And they made up something else. But at least what they had right is to understand that the problem is to see, does it go one way or the other at a beam splitter? And also, if you were to reconverge the beam, would you see an interference pattern? So that's the part they got right, that it's both the particle part and the wave part to try to understand what's happening with quantum mechanics. But they did this part wrong. There's no pulse height resolution. Nobody in any of these experiments before me looked at anything to do with the pulse height that can come out because it's a photomultiplier tube. But first, let me just say, after the French team, ASPE, other people did it the same way with the triple coincidence, and they still used the wrong chance equation. They understood that this might be the right chance equation. They cite it, but it didn't work for them. They threw the correct triple chance equation, triple coincidence chance equation. They threw it away and did something else. And I say no fair, using the wrong equation for this experiment, because they wanted to see that it was even less than chance to go one way or the other at a beam splitter. So who did these experiments? Here's the beam split. It could be done another way, where there's a thin detector in front of a thick detector. And I did it both ways. So who did these? With visible light, that's what everybody else did. I'm the only one to attempt this experiment with gamma rays, and I see it in both of these geometries. And this is the true coincidence test that is a control to see if you emit one at a time. And all the nuclear physicists understand how this works. They use it, and I agree with it. Everybody agrees with this, the way this works, the true coincidence test. With alpha rays, I'm the only one to attempt anything like this, to see if there's a one way or another effect, or a both ways at a beam splitter. It's just me doing the alpha rays or gamma rays, and to look at pulse height resolution in any of these tests of quantum mechanics. So, like, I'm talking about pulse height resolution. This is what a photomultiplier puts out, and it's a wide distribution. The problem is they don't say where they're using the pulses. Where are they setting their pulse height filters? There's no mention of where they set it. So I don't know what they're doing. But you don't have that problem with gamma rays, and everybody sees that there's a pulse height resolution that is proportional to electromagnetic frequency. So on the horizontal here is how big are the pulses, and that's the same proportional to electromagnetic frequency, and the same thing as proportional to what we call h nu, the energy of the detection on the horizontal. So you do have pulse height resolution with the gamma ray, and you could say, oh, we're only going to look from here on and look at the big pulses and see that we get 2 for 1. But nobody talks about that for any of these other tests. So they sort of all miss the point. To them, it's all photons. They're all the same energy because they use monochromatic light, and they look at all the, I don't know where they do the clicks. I don't know. They don't say what part of this spectrum they use. But with me, you could see everything. So this is my invention. You take some account as to what are these pulse heights you're going to use that you're starting with. You do a background test. And when I do this with alpha rays, I'll see 1 or 2 over the whole day. And you could take that number and subtract. So then you do the true coincidence test with the same detectors, the same setting, and you see, well, does it emit one? You'd get chance here if it emits one at a time. Or if, does it emit two at a time? You'll get a peak in the time difference histogram. Or you could calculate it out and compare it to chance to see the same thing. So if you see that it does one at a time, then you take that radioisotope and then rearrange the detectors to either the beam split geometry or the tandem geometry and do the same test and see, did it go one way or the other? Does it look like just noise? Or does it go both ways and do you see a peak? I'm the only one to see a peak in this whole class of experiments. Everybody else sees noise or argues it away somehow by whatever. So yeah, this is my invention. So this is how I do the experiment for both the alpha ray splits and the gamma ray splits. So I'm going to show. All right, this is nuclear physics, and they generate these energy level diagrams because they do the true coincidence test to tell that this is one at a time, one at a time. And the half-life of americium is so many million years. I mean, oh, I'm sorry. What the half-life of americium goes to Neptunian, which has millions of years. And so if it was to decay again, you won't see it. So it's a one at a time source, and I test that anyway. So just a quick review. I mean, I showed this in previous lectures. This is the electronic setup. This is the whole setup that I use for both gamma rays and alpha rays. So there's detectors, amplifiers, pulse height filters, which are nuclear instrumentation, NIMBIN things, professional modules for all these, pulse counters for counting the pulses that come out of the filters. So this is the rate in the first detector, the rate in the second detector. And we're going to use them in this chance equation. And then it goes into the trigger system of this LaCroix oscilloscope is able to make a histogram to trigger within a time window that is preset. Let's see, where is it? But we're counting within this 300 nanoseconds. So we're going to look at how many happen in the experiment within this time window of 300 nanoseconds. And that goes into the experimental rate. And then we compare to chance. The rate in the first times the rate in the second times this time window. The time window is the same one we just used over which we count. And so this method, I'm saying, that's the same thing that three other tests have used and described. And when you compare the experimental to the chance rate, this is about 6 times chance, which is completely great. And I've seen this many ways, and it's full height pulses. I set the discriminators here so that it's 2/3 from 0 to 2/3 of the characteristic pulse height to say that these are all, this is the pulse height histograms. So you get to see the pulse height histograms and the timing histogram and the analog signals all together when you run this oscilloscope. And I developed this technique of how to see this. So being above chance under these conditions, the photon is dead. And there's a detailed video here to see how I set everything up that can be clicked from my lecture slides. And also there's a video showing how the pulse histogram in time lapse that could be seen from this video. So why was it never seen before with the gamma ray is that I discovered the photoelectric effect has to dominate over the Compton effect in the detector. And also, you just have few to start with, and you have to know what you're doing. Most people are working up here, and you'll just see quantum mechanics. If you were to just look at the pulse height spectrum and look at accidentals overlapping and stuff. And they do calculations in the textbooks. And so you have to know where to look and how to look. So I discovered how to do this. And then I went and I devised all kinds of ways that you can see functions of angle and temperature and whatever, all different ways to use this. So now back to the alpha ray test. So what I have here is that a radioisotope of americium emits an alpha ray, which is a helium nuclear matter wave. I say they say it's an alpha particle, but if it's a particle, how do you get interference effects? That's the paradox. I'm saying it's not really a particle; it's a matter wave. And so the experiments are my attempt to show the distinction. So what we have is that the alpha cannot go to this detector on the right where it picks up the reflection from the gold. So I suspend a gold leaf over this detector. Now, some of the alphas will go through and make a click, and some will reflect and make a click. But when it goes to both, I read it in the coincidence triggering system. And you might say, well, what if I'm looking at half height pulses and I'm splitting the alpha into deuterons or something? Well, that cannot be, because other experiments have shown that it takes to split, you'd have to have a total of 14 MeV, 7 per deuteron. You'd have to have more kinetic energy than what we are starting with. We have 5.5 MeV in emission from the radioisotope. And I did the true coincidence test as well, and they did. Everybody agrees it's one at a time. The pulse height histogram is this great big peak, and I did all kinds of shielding experiments. So what's going on is the question. So this is going all the way back. I did these experiments in 2006, and now I'm returning to it to see if I can get extra information. And I was very careful about the pulse height spectrums and everything to try to sort it out. How big are these pulses? What's going on here? So this is inside the vacuum chamber with two small detectors close together. The gold is on this side, and the alpha ray can either go through or split. And so here's what it is. The pulse height I'm plotting is on the horizontal here of this first detector. The pulse height of the other detectors vertically. So I had to automate the LaCroix oscilloscope through the computer. It was very difficult to do. And I don't really care to do it, to even try to make it happen again. But I managed to do it. It took months to program it in 2006. Oh, about a month. So here we can see most of the pulses are half height pulses. So it's about seeing what is the relations. Do I get a half and a half? Do I get a half and a full and a half? How is it coming through? They're coming through where they're pairs, half and half, or full and full. When you calculate chance, this was 100 times chance for the half height pulses. The full height pulses was 4 times chance. That is completely great. This is my strongest evidence. The pulses are all perfect. There's no overlap or noise or anything going on. There's this great big delta time difference histogram. We see everything. So now I've returned to it, and I went and I built this more elaborate system where I have control over the angles with stepper motors on to control the angles of the detectors, both detectors, and to motor drive it from computer control to scan through. Now, I've not done this scan yet. I've only done some spot checks to see what I can discover. I'm going to show you my recent discoveries by looking at angles. And I made an important discovery. Well, first, let's just see what happens in the conventional way that I do this with a gold foil and americium and inside this vacuum chamber. And in this test, it was 37 times chance. There's this great big peak, and here we can see the pulses that come through. So there's a wide range of pulses. You could see that most of them are like half height pulses. And then there's bigger pulses. And we can count these bigger pulses, and they're all in time with the other one. The other one has bigger pulses too. But let's just say these are half heights and these are more than half. And you add that up and you see, well, what kind of degree above chance am I going to have? And that's 5.5 times chance, which is completely great. That I'm saying I'm doing more than 1-to-1 in energy, and I'm doing better than chance. So that's the argument. I'm doing both a time budget and an energy budget. And I make this term about energy conservation. Everybody will talk about this energy conservation in terms of particles. They're sort of missing the point. So I'm saying when you read people talking about energy conservation, it's really a particle way of thinking kind of energy conservation, and that there's a generalized energy conservation that will include this preloaded state that nobody thinks is there. So I'm showing the distinction between particle energy conservation and generalized. So I'm saying I exceed particle energy conservation when I do these analysis of full height pulses of more than half and half when you add a half height and more. That's what I'm talking about here. So now I'm getting to angles. So I do for the first time, when did I do this? A few days ago, August 19th. I collimate the source. This is a stronger source. It's a different source. It's stronger, and it has a wider pulse height spectrum. So it's a bit in my way in the pulse height spectrum. But it has an angle effect. So we aim it. I'm aiming now at the detector without the gold because I want the crystalline property of the reflector to see if I can do like a Bragg scattering off of the periodicity in the nuclear realm. I'm trying to discover it. I'm predicting I would see this angle effect, and I see it. So this is a major discovery that when you do, I just guessed here at 30 degrees. This is my first test. And what's important about it is that the noise in the histogram on the sides of the histogram, they go away. It's all in the middle of this great big peak. And you count that and you see, well, how many happen in this peak? 670 times chance. That's a record breaker for me at 30 degrees with all this setup. So I go on and I say, well, let's change the angle here. So all I did was twist the source over to what looks like 45 degrees. I left everything the same. The effect goes away. No peak, a bunch of noise. There's no calculation of chance even. You just see it's chance. These vertical lines are normalized. That's each of these little lines. It's hard to see. That's a pulse pair, a detection coincidence click. And so it's not making a peak. And so then I go, well, let's go back and see if I repeat. It does. So I repeat this angle effect, going back to what 30. So I'm going to automate this. I didn't control the angles by computer yet. This is just hot off the presses to just twist it around and see what I see. And I see it. That what goes back to close to 30 degrees, the it's hard to see. There's a great, I'm going to show it. It's still on the screen here. I'm going to be able to show it on the LaCroix screen. It's still here. So let me go back. I'll go back to the screen to let you see the LaCroix screen closer. But we're able to analyze the pulses that are bigger than half and count them and do a calculation and see this is 3.2 times chance for where I'm doing better than what I call particle energy conservation. I'm adding the pulses to be more than one. Starting with one and getting one, well, I get 1.5 approximately in this kind of test. It's kind of fuzzy in that, well, how much above chance, above one it is. But we'll see how to make that better. It was 142 times chance. It's not set up exactly the same way. I just twisted it anyway. But the important thing is the noise in the wings of the histogram, this stuff on the sides, they went away. It's a perfect peak. The noise, the out of time coincident pulses go away as a function of angle. So whether it's on quantum or not, it hardly even matters. It's a discovery of a new probe of the periodicity of what I'm scattering off of in the nuclear realm. So still, you wonder, well, what is causing these half-height pulses? In the case of gold, can I be pushing gold? It's not likely, but that's about all you're left with if you're going to try to make a particle argument out of it by looking at half-height pulses. Because we're not splitting the alpha, we're not splitting gold or the silicon or anything. We don't have the kinetic energy to do that in a conventional sense. And also, can a particle model explain an angle resonance like this? Well, you'd be hard pressed to do it. But that's kinds of future arguments where I expect people will try to shoot me down and say, oh, Eric, maybe I'm just seeing the probability model a different way. Well, if you go back to the way I did it here, this eliminates that because it's clearly 2 for 1. But now I have this added effect of angles. All right, so there's more. I split the alpha off of diamonds. They're half-height pulses, but it was 8 times chance. So what would do that? I did it a few different ways. Here's the split. And here's all the beautiful pulses that come in coincidence. So we're not splitting carbon. We don't have enough energy to do that. We're not splitting the alpha. It's going together to both detectors. So here's what's interesting about the diamonds. I did a pulse height spectrum, just normal spectrum. And I had a good resolution. The resolution of the spectrum depends a lot on the source. The newer sources from a smoke detector have a better pulse height spectrum than the older sources, which are stronger. So that's part of how to understand what I'm going here. There's this great big peak at 5.5 MeV, they call it, just in the pulse height spectrum. Then reflecting off of diamonds, there's a dip. There's a resonance with carbon and against the alpha from americium, which is an incredible serendipity. And I want to take advantage of that. And so I looked at what's his name? Michael Perrone has graphene. So I'm asking Michael, can you send me some graphene film to use as a beam splitter? and we can work. This is a way we can work together to develop this unquantum split more. because of this resonance and the way I found it works off a diamond. So we have good evidence to go from. This is another test where I tried to make fractional charge, and I made a mass spectrometer. This is a big magnet, and the alphas go through and deflect. I saw all three charge states, but this is two of them. And I tried to influence the charge state of the alpha with an electron gun to make this dip go away. But my electron gun wasn't, I had to build it because it was in a range. I couldn't buy it. They didn't make what I wanted at that low energy to make a velocity resonance. This is a miniature version of the alpha split. It's hard to see. There's a detector here and a detector here. It's on a NIM module that I modified, and that's my laboratory. And so this is a whole list of a partial list, really, of the experiments I did with the gamma and the alpha. And it's important to see a little bit of theory. Planck is thought to have quantized energy, E equals h nu, but he really had his h nu in matter. But more importantly, his second theory in 1911 was that his constant was a threshold, not a quantization. And from that model, he derived the black body equation. And he drew in his book about this loading theory, that it loaded up and it had this sudden emission. The loading theory was developed first by Planck. And I take off on this idea of H being a threshold, and I apply it to the other constants, the charge constant and the mass constant. And I look at the equations. This is my theory. Look at the equations that are famous for showing wave diffraction, wave effects. And let's take this one for like the de Broglie equation and matter wave diffraction. It has the ratio h to m. The message of the experiment is the ratios of the constants, and the same thing with these other experiments. It's the ratios that are quantized. So all I'm doing from the left and right column is to rewrite the ratios of the constants as a Q and say that's the message of the experiment, and that is these ratios. The theory is that it's the ratios that are quantized when you see wave effects, and that's because the constants, the chargedness and actionness and massness that's spread out in a wave is actually less than the quantized that you think of. But in the wave, it's the ratio that's conserved. When you see wave effects, it's a principle of conserved ratios that I developed to understand how can helium smear across space, show itself as a wave, transmit its identity. This is how, because the ratios of the matter wave are conserved. It can transmit its identity this way, the same way with charge and protons and neutrons and whatever, that the ratios of that matter wave go across space. So this is really the important part, how it could be to even think about what I'm doing experimentally. And so I do. And then, this is the craziness that everybody is led to. And I'm saying, look, please, let's be real here and look at it. What happened was this beam split experiment, the one way or the other, they think it's right. And they think the probability interpretation and quantum mechanics is a done deal. And then they apply it to the understanding of their two-particle experiment. I have to call it something. And then they did the experiment right, and they see it's different from Bell's theorem. But Bell did not include the idea of a preloaded state. And so that's where I'm identifying how to clean up the whole mess. Bell is wrong because he doesn't include the preloaded state, and quantum mechanics is wrong because they don't include that state in the detectors. But it's confusing because this experiment gets the right answer of the curve. But if you look at it closer, you could see why they get still the right answer of the curve. That's why it's confusing. So that's now I'm going to try to look at my camera. You see, it's very difficult to do a demonstration of the experiment because it takes 5 hours to do it. But this is the result of the experiment, and the numbers that, I mean, this is just right hot off the presses. The numbers that came off, I write down on my pen board here that the calculation of what just happened. But these are the half height pulses. This is the 142 times chance, and so back to the LaCroix screen. What I'm going to do is I want to just show that the wings here of the histogram, where it's out of that it's not in a peak, that it's not within the time window of which I just calculated chance. What's going on in the wide here? This is what's important about this angle effect. It makes the out of time chance pulses go away. I'm going to try to go over to the oscilloscope and just change the scaling of that pulse height histogram, and so yeah, it's this great big beautiful peak. I narrow it down, and then to the right of the peak, you'll see like 2. All right, well, yeah, you could see it on the time graph. There are these 2 that's at it. So it's only really, and then there's another one to the left. There's 3. There's hardly anything out of time on this experiment. And so you get to zoom in on different ways on the oscilloscope, and you get to count whether I'm in this, whether, let me go back to the mouse. I get to count what's in the pulse height spectrum, how many I count that are big. I get to count. This is the other pulse height spectrum of the other detector, and so you can. It's hard to see, but it is here. There are the pulses of the other, the bigger pulses. You get to see them, count them, whatever. So the way the trigger works. Let me turn on the trigger system. It's kind of hard to understand, but I'm going to show anyway, just quickly, the way it works. And I discovered that the LaCroix had this method, and it's just completely great that it lets you do coincidence experiments. You trigger on channel 4. The square wave pulse is from the NIM modules, which read within the pulse height range the time as to, and you get to use a knob to push wherever it wants. It's a relative time between the 2, this square wave and the other square wave. So is a time pickoff electronics, and it reads the time of this square wave, and it says trigger on 4 after this square wave goes after 3 triggers. And then it reads the histogram delta delay between 3 and 4 and plots it on C. That's how, very quickly, that's how the trigger system works. And all this great data that you get off the LaCroix oscilloscope, see everything in the experiment. And so I have another setup to show pulse heights. And if anyone wants to interrupt and say, oh, Eric, let's try this or that, that's okay. But I'm going to, so this detector is, it's the opposite polarity from the other ones. Anyway, it makes a negative pulse, but I straighten it out and I redraw it. There's a feature that lets me do that here in the LaCroix. And so there's, let's do a close-up of what is the source. The source is these 3 little dots, 4 dots that are taken out of the smoke detector. And so there's the americium. These are good sources. There's a very thin layer that protects it so that the pulse height resolution is pretty good from this. And so now I'm going to take away, let's take away the persist and get it started from the beginning. So you could see it makes pulses. And let's clear it to start the whole thing over. It starts the pulse height spectrum. So that's what it is. It's pulse height spectroscopy. And so this is all well known for both, mostly with gamma rays, also for alpha rays. Anyway, I'm generating the pulse height spectrum, and the trigger is at about a half height place now. Can you see the screen? Oh, sorry. Okay, thank you. All right. Sorry about that. The trigger, I hope people hear me. I can't tell if you're really there. So we're triggering on half height pulses and doing a pulse height spectrum. And that's what alpha ray pulse height spectroscopy is about. So I wanted to have something real time as to what's going on here with the experiment. And now I can show the let me pull the camera off, and so I can do this too, and go to the actual experiment that I'm so proud of, that I was bragging about just a minute ago, and go inside the chamber. And so there's the 2 detectors. It's hard to see. My photography of it is a lot better. But there's the 2 detectors, and there's a source that is aiming at the left side. And the LaCroix screen, the some mess of so if there's anything anyone wants to see me do, I could consider doing it, but I prefer to not mess up this nice peak. It's very easy to lose it, and but I could zoom in different ways on any of the spectrums right now. But anyway, that's the setup I have, and this is a lot of work. So I want to, let me just let me go back to the webcam and myself, and open it up to any kind of questions. How much time do I have? I don't know what happened. Is anybody there? What happened? I can't tell if anything happened.
Wait, can you hear me?
Yes.
Okay. Okay.
Now I
Yeah.
can.
No, you got about 10 minutes left, sir.
Oh, good.
Yeah. Yeah. Well, I'll tell you what, let me bring the guys in.
Right.
Bring Jared, Joel. Here, I'll bring the fellas in. And yeah, we'll open it up for questions. Guys, any questions for Eric? And Eric, thank you so much for that presentation. You know what? But actually, before we do questions, in true to tradition, let's put our hands together and give an enormous applause to Eric Reiter. So, okay, you scared me for a minute. I've been having broadband and equipment issues all week. I have new internet being installed next week, so we'll see. Okay, go for it, Jared.
Yeah, Eric, excellent presentation. I know I'm going to have to go back through it a couple of times so I can fully digest it. But I just wanted to try to get explain like I'm 5 and how it relates to propulsion. So correct me
yes.
if I don't understand this right. But if I understand it right, traditional quantum mechanics is saying stuff is discrete. You get these discrete chunks of the energies. But what you're demonstrating is no, it looks like there's more of a continuous nature to everything. And it's just the detectors are detecting things in discrete chunks, right?
Right. It's not just the detectors, it's matter and energy in general, the way it works. And that there's a sub quantum that it's like what I tried to do with the cups. Everybody thinks it's quantized as if it's full or empty. I'm saying there's a partially loaded state. The way it relates to propulsion is to understand dark matter and dark energy. What is it? I'm showing it. It's the partially loaded state that must be there in order to have the results of my experiments.
And if we were to tie this to propulsion, having this more continuous nature, if there's a way to tap into that continuous nature, it means we can take the photon rocket model and go, wait, let's put some gas on that fire and let's get some actual usable thrust out of this thing. It improves the photon rocket model by many orders of magnitude.
You get to do sub-quantized, sub-photon state interactions. It opens the possibility for that because now you know what it is, that it's not quantized energy in space like that at all. It's just the illusion of that when it interacts with the detectors to make it look like it all shows up at once. But it could really be a threshold. You see, the threshold model embraces what looks like quantization, but there's a distinction. Quantization excludes the idea of a preloaded state. Thresholding includes both a discontinuity and a continuum underneath. And the experiments is the way to see that it's really a threshold model. Next.
Okay. And you know, something that occurred to me, and Eric, I don't know if you'd be up for this, but you know, when we started APEC, we used to do we had a couple of 3-hour presentations, and most people couldn't fill that. And so then we took it to 1-hour presentations, and now you're kind of overgoing that. But I thought, you know, and like with Jack, we're talking about doing this also, having a breakout session, like literally just a Zoom call where you could run through the whole thing from start to end for a couple of hours, and we could just do Q&A for as long as you want. That's something I could set that up if you wanted and send out an invite for it.
That's good. I'm up to that. I
Yeah,
went through the
okay.
slides. I went through the slides quickly.
I
I could
know,
do it.
yeah. And and that's that, you know, but it's one of the challenges trying to do, again, it's you know, it's like you're gonna it's not gonna work for everybody no matter the way we set it up, right? So, um, But that occurred to me when you were going through it because you have so much detail and depth in the work that you've done that for you, an hour is like a real squeeze, right? Like
Yes.
another person, Jack is like that. Bob Greenier is like that, right? There is so much there, and then, but for most folks, it's like an hour that's about all they can do, and that's not negative. It's just, a lot of it is depth and what people are willing to present and how much energy they have. So, you know.
Well, thank you for that idea. It'll be great fun. I'd like to give it a try. Yes, any kind of session with you, I'm up to.
Yeah, yeah. It's just kind of a thought that came to my again. It's kind of the same thing with Jack. He did that open mic the other day, and I think he talked for probably 3 or 4 hours straight. And and like not everybody has that level of focus, but there were people who were with us the whole time, and it was like, okay, you know what? We should set something up and record it, and it would be the same thing for you. It's like, let's carve out a Zoom session. You guys can go as long as you want, because I mean, hard drive space is basically free, so why not? And I'm just praying that this is something I can't tell. Maybe you guys can tell me. Is my mic way too loud, or is it kind of a normal volume?
It's good to me.
Okay. I upgraded. I'm doing it's called the Shure MV7 Plus. I just upgraded, and it has an auto volume on it. The old one I had to, like, set, and I kept playing with it. This one supposedly sets it for you, but I have no idea where it's set, so You guys have any other questions for Eric?
I have sort of a half statement, half question. The concept of the threshold reminds me of, like, because I do climate research, it reminds me of a tipping point. Although a tipping point is a threshold that's an irreversible change. It's over at that point. So
That's right.
threshold is a little earlier in the process. Another question is, what is the mechanism determining where the threshold is at, or is it just sort of like a self-regulating change?
No, it's the same place you'd see in normal quantization. Planck's constant is an important number. These numbers are right. It's just that I'm reinterpreting them as a maximum, the way Planck did in 1911. The threshold is Planck's constant, the mass constant is the charge constant, but those constants are about maximums or tipping points. That's a good word as well. But it looks like quantization, and it's easy to think that way. But if you think of quantization and then doing particle diffraction, you're lost. It's in paradox, and you have entanglement and all these problems. But the problems go away. The ghost waves go away with a threshold model. It's always been
Yeah.
a problem, like how do you show the distinction between the two models? And that's what I'm doing. I have it very clearly distinguished with the gamma ray split. The alpha ray split, I admit, can still use some more work, but I'm well on the way of showing it. I mean, I have good evidence, but I'm going to do it even better. I'd like, as I mentioned earlier, I'd like to find some graphene film to do the beam split with, because I found a carbon resonance. I think it would be a better beam splitter than gold, and to do the angle effect. So the question is, can a alpha ray with a model of probability, can an alpha ray do an angle effect where there's some angle that's special? Can there be a special angle in a reflection where it'll do a split? Can a particle probability model do the same thing where can a particle probability model do the same thing as what I see in my experiment? And so what I'm going to do now, where I can automate the experiment, is carefully show different angles and see how that affects it, and get, well, I'm going to do a calculation to see if I can relate it to layers inside. It's a probe of the nuclear realm in terms of not probability, not particles, but like layers of standing waves within this nuclear realm. Now, I made that work with the charge wave, with Compton scattering. Compton scattering is with a gamma ray. It's Bragg scattering. It turns out that Compton actually did that in his book. It was a bit clumsy, but I cleaned it up and did the same derivation, where the wavelength of the X-ray or the gamma ray does a Bragg scattering with the material. In this case, it was the electron. Well, I'm trying to see that now with a much shorter wavelength of the alpha ray doing Bragg scattering in the nuclear realm. So I'm inventing this nuclear alpha split spectroscopy, and I have the first evidences of it. I'm very happy to see what it was just a few days ago. I mean, that experiment that I just showed you, that's just a few days ago, and I didn't even want to turn the oscilloscope off in order to show that it was really there.
Yeah. Well, and guys, let me see. So we're at the top of the hour. We should go. I'm going back and forth on this. We should go to and do a tribute to Jim Woodward. David Jenkins is here. He has some words he wanted to speak about him. I have some photos I can share. Curtis just texted me. He said that he would not be able to make it until at least after 2, and Jack will be presenting at 2. And then Michelle actually tried to log on, and she was having technical issues. So I don't know. David, what do you think? What should we do, sir?
It would probably be better for Curtis and I to go sequentially, then it would be more continuous about Jim.
Okay. I mean, if for something like that, we would want to push it back until probably 3, until Jack is done. Do you guys want to just do Q&A with Eric for another hour, or?
I'm up to it. I'm with you. That's okay.
I'm trying to make everybody happy, which usually means everybody gets upset with me.
There's a lot to see still. I mean, I could adjust. I could show alpha ray spectroscopy or the slides, whatever you like.
I'd like to hear, if we got a little more time for Eric, I'd like to hear more on how you envision your observations and your model, how you could apply that into propulsion, right? The P of APEC, right?
Well, if it's okay, then let me ask David, since you did have stuff that you wanted to speak about, would you want to come back in later today, or should we split things up, or how much time did you want?
No, it's okay. I always listen to APEC. It doesn't matter.
Okay, well, why don't we go then, and we'll push things back today. We'll just kind of. Okay, well, I owe everybody an apology again. I'm trying to juggle. I've had like a bunch of last minute changes. So yeah, Eric, if you're happy working with stuff, I can leave everybody else up on the screen, or bring them in, or you can present more.
Let me just say a little bit about propulsion. I don't know just how it will affect propulsion. I don't know. If I knew how, I would be driving my flying saucer. But what I'm trying to give you is what the matter wave is. What is matter and what is energy as a starting point for your theories and experiments to then get it right for doing more propulsion ideas. I don't know how to push against this matter wave yet, but at least I'm showing you how to get away from the paradox of wave-particle duality and to explain what dark matter and dark energy is. So Yeah, I'm only going so far, but it's an important step. It's one step at a time to do good physics.
Yeah,
But
I would say, guys, why don't we run with it then? We'll run with it until 2, until Jack comes, and maybe I could bring Dan. Dan, can I bring you back in, sir?
Hey, Dan. Hey, Eric.
Yeah, and I would say if you guys are open to discussing it, and then I will, if it's okay, I'll just take myself out, and you guys can just run with it for the next hour or so.
So, Eric, you mentioned graphene. We have graphene, but you can get it pretty cheaply these days from a number of places. There's like a $50 for single layer graphene on a piece of quartz, depending on what you need.
Well, all right, that's not quite right. It needs to be a thin film, like the gold leaf, where I can see what goes through and reflect at the same time. So
Do you need freestanding graphene or what?
That's right, freestanding.
All right. Well, we can talk about that in more detail afterwards. That's more of a challenge.
That's right. It doesn't have to be monomolecular. Something of the order of what gold would be with gold leaf. The way
so like a graphite foil?
Yeah, but thin enough that alphas can go through it.
That's quite thin.
Yes, it would be.
I'll see what I can do.
Yeah, that's right. So if it would be empirical. You'd give me something and I'd say, oh, well, alphas don't even go through. I'll see maybe what reflects, but it wouldn't really fit the bill. And then you'll say, oh, well, I'll have to make it thinner. So I don't know how to tell you yet how thin it would have to be or even how to measure it.
Well, my recommendation then is to purchase some Sri Lankan vein graphite. It's more structural than pyrolytic graphite and has higher crystallinity. So you can really cut thin layers off of that. And you can use the tape method over large surface areas with it.
No. The tape would get in the way.
Yeah, but you could just be
I don't know how to take it off. You have to tell me how to get.
But there's ways. There's ways to do this. We should chat about it more afterwards.
All right.
I'm curious actually about that setup that you had. So are you doing some sort of interferometry here or just the spectra?
Well, it's let me get my camera to work. It's not interferometry. It's beam split coincidence experiments. So
gotcha.
The slides. Let me show the distinction. Thank you. All right. Interferometry is if you were to reconverge the beam and see this is an interferometer. So I'm not reconverging the beam. I'm just looking at the timing between what happens at either side of the beam split.
What are you using as a beam splitter again?
I'm either using gold foil or the detector itself for alpha rays.
All right.
So there's two classes of experiments I have for alpha rays and gamma rays. For gamma rays, I can use a thin detector, or I've done it with slabs of germanium and aluminum. I've done it with several different materials, but the best one that I have is to use a thin detector in front of a thick detector, and that does the beam split. So the detector, serves a dual with a gamma ray. The detector serves a dual purpose of splitting and detecting in this geometry. But I have done it where it looks like a beam splitter with germanium and silicon. And detail is in my previous lecture that I did on this venue, where I showed the details of that. Let's see, I might have that down here in a slideshow, but that's the gist of it. So for the gamma ray, it's beam splitting and looking at the timing between the pulses to see if it goes one way or the other. And for the alpha ray, it's a gold foil, typically. So I've done it with the alpha ray I've tried all different kinds of foils, whether it's high purity gold or 23 karat or whatever. 2 layers of 24 karat gold works really well. And it's like I tried it with copper and palladium and silver. It doesn't work as well. So it's a beam split coincidence experiment, like I was showing the whole history of, to see the particle part of Einstein's model of the photon. And so that model also applies to anything, whether it's light or charge or whatever, to see if it goes one way or the other at a beam splitter. And so the most recent test I did was off of the crystalline surface of the detector itself. And that's what gave this important angle effect, where the angle of incidence against the splitter matters. I saw that for the first time just this week, to be able to see that kind of spectroscopy. And that's like the closest thing to that is like X-ray diffraction crystallography, where they're able to see the periodicities of crystal structure in whatever they're putting there. That's how many of our drugs have been figured out, by getting the shapes of protein.
In theory, you could do crystallography with these other particles, I guess.
That's right. With the other matter waves, with either light or matter waves. Yes, I just discovered alpha diffraction crystallography.
Fascinating.
Right.
All right. Well, I understand that a bit better now. I am curious, though, if a full interferometer could be made using matter particles too. But how will you do it? It's difficult because you need the beam splitters and you need some sort of mirrors. With the alphas, they have a charge, so maybe you can redirect them with electric fields.
Well, you already know
their energies.
You don't need to do interferometry. You already know it. You already know that it has a wave property.
Well, I was thinking along the lines of instead of the LIGO detector, you use matter, like the wave properties of matter, instead of the wave properties of light, to make an interferometer.
It's hard to get a second reflection. It's hard enough to get a first reflection, and then to reconverge it again. That would be so difficult to do.
All right. I mean, so not practical yet.
Jumping ahead.
Yeah, not practical yet for that. But this is already
ahead.
telling us interesting things about the physics involved, though.
But realize this, that just diffraction of the matter wave was understood, well, with electrons all the way back to Thomson and Davison and Germer and Esterman and Stern in 1930 to make it fit the de Broglie equation. So we already know that it acts like a wave. The interferometry will just show that it acts like a wave. We already know that. We could see the wave effect without a Mach-Zehnder interferometer. You just use a single reflection, a diffraction grating kind of interferometer. I mean, it's not an interferometer. To just use diffraction instead of interferometry. And so you get all kinds of information out of it like that. So that's what I'm discovering how to do with the alpha ray. It's an alpha ray diffraction effect off of the inner structure of the nucleon.
Oh wow, that's actually really interesting. So, in principle, you could actually. That's really cool because we don't actually know that much about the nuclear structure. Like, there's a lot of like quantum chromodynamics, but like even the quantum chromodynamic models have somewhat limited predictive power in some cases. So, if we could get hard data on what the nuclear structure is like, that would be a big step forward.
Yes.
I know they were studying.
Yes, that's why I'm excited. That's right. This is a big step forward. This is angle
really cool.
Angle information on the nuclear level.
Very cool. And then you could use like dynamic nuclear polarization to align the nuclei to get a better, like in a X-ray crystallography, you make a crystal of something. You could like align the nuclei with dynamic nuclear polarization to get a better image. Probably.
Well, maybe. Look, what I'd really want to do is get better detectors, higher resolution, maybe cool the detectors.
Okay. This is definitely worth a lot of follow-up on the engineering side. We'll talk.
That's right.
Yeah, I think like even like with the uranium atoms, they were talking about what was it? Nuclear molecules, like inside the nucleus, like certain excited states where like inside the nucleus, like chemistry could happen, sort of, among the nucleons.
Well, I expect the periodic structure in the nuclear realm to be echoed by the larger crystallographic structure between atoms. I expect there to be.
I'm hoping it's more interesting, but certainly
whatever. We'll
might be
find
more like protein crystallography.
By what?
It might be more like protein crystallography. You might see some weird things. Depending on the
protein is about spacing between the atoms. That's the protein crystallography.
Well, I'm sure there's non-trivial nuclear structure, is what I'm saying. Like in a protein crystal, that's very you wouldn't guess a protein crystal, but you could see what a quartz crystal. You could visualize what a quartz crystal is like because it's very predictable. But a protein gets a little weird, and especially for the heavy elements, that nuclear structure could be really weird.
Well, I don't know if you really get it. The crystallography of proteins and crystals is about the spacing between the nucleons with an atom model, layers of lining up atoms. But this has such a shorter wavelength that it's out of the range of the spacing between atoms.
I'm making an analogy between the nuclear structure and the protein structure. The nucleus. Yeah. The nucleons might be arranged in more complicated ways than a simple crystal lattice.
We'll find out.
That's
We're going to
exciting.
find out the crystal structure in the nuclear realm with this coincidence technique where the angles matter so strongly. I mean, this really surprised me that I changed it just a few degrees off. The peak went away. All I did was rotate the source. Kept everything else the same.
Are you sure that's not like the most likely thing is you're rotating the nuclei are usually randomly oriented relative to the crystal lattice. Maybe there's some like orientation along the crystal lattice, but the big thing you're changing is the electronic lattice, not the nuclear lattice. So maybe it's electronic diffraction still.
No, the wavelength is too short for the alphas to be doing any interference effect on the electronic level.
So that would suggest that there's some correlation between the nuclear alignment and the crystal alignment on the electronic level.
I do expect that. I do expect a relationship like that between scales of size like that they'll affect each other.
Because usually the nucleus is thought of as something it just rotates randomly, orients. The nuclear magnetic moment is so tiny, so it doesn't usually orient with the lattice, and it's weakly coupled to the lattice. So, but that suggests strong coupling between the electronic and the nuclear lattice.
What it looks like I'm resurrecting J.J. Thomson's plum pudding. Is that the nucleus does not need to be a small point, that it could be extended and have more interaction with the matter wave.
Interesting. Very interesting. Well, I'll let someone else ask a question, but let's definitely catch up soon, Eric.
Very good. Thank you. Good. So the angles here are wide. I'm using these tubes, which is like a half a millimeter, about a millimeter in diameter here for the aim. So there's an angle spread that I'm not showing. And it's hard to get it narrower. You lower the count rate. But with this kind of aiming system that I just recently devised, I'm able to see this effect. We're just twisting this source over, makes this big difference. So the crystal stays the same. It doesn't matter so much where it is. It's too small. So yeah, you had good ideas.
I think you should try this with Mark Sokol's lab has dynamic nuclear polarization capability, so you should try doing this diffraction experiment on something that is being nuclear polarized to see if it strengthens the effect.
Look, I don't really know what you mean. If that's inside of a magnet or what, like electron spin resonance or NMR. I don't really know what you mean.
Yeah, basically all the nuclear magnetic moments are aligned.
Yeah, but that's really hard to do, to have this inside of a big magnet. I am capable of making a magnet. I was able to see the 3 charge states of the alpha.
DNP is frequently done in labs. It's heavy equipment, but like certainly if you can find someone to work with who has a DNP source, you can. I know there was like some of the national labs got up to like 90-something% like polarization, which is really impressive. So
look, I'd be happy to just bounce off of different crystals at this point.
Fair. That's a good place to start. It's an easier experiment.
And so I've bounced off of diamond and silicon crystal and gold. Now, gold is amorphous, and there's a big difference in what happens between the out of time pulses are much more with gold, and so they go away with this kind of crystallography.
Gold is polycrystalline, not amorphous technically, but it might be nanocrystalline, and that could definitely throw off some diffraction stuff.
All right, nanocrystalline. All right, good. I don't. Yeah, well, thank you. Gold splits the alpha.
Right.
That's where when I did this was really my best test, where I was able to see the full height pulses.
Well, actually, gold still forms crystals, so that's interesting that it's amorphous. Maybe that has something to do with the electronic structure, because the alpha is interacting strongly with the conduction band.
Well, I think you dropped out. Something happened. I don't think it's electronic at all.
I'm back.
I don't think it's electronic. It's all nuclear to me.
Well, I mean, it'll be a little of everything if the size scale is that small. But anyway, yeah, I mean,
you're dropping out.
Eric, can I jump in here while we wait for Michael's signal to come back?
Sorry about that. Yeah, my signal's off and on today.
Michael, can I jump in here?
Sure, go ahead.
I wanted to try going back to the propulsion side here for a second. I know that Eric, you said you haven't really gone down that path very far because we're still in the preliminary. Is it a thing? Not how can we use the thing, right? And it looks like you've proved it is a thing, but getting to that next hurdle of how do we use the thing? If I understand it right, though, your model showing this continuous versus discreteness and how you might use that with matter waves, it seems like for a photon rocket, that this might be a way to slightly improve on photon rockets. Alternatively, could it be used on the matter wave side? So rather than throwing out photons, we're throwing out, ions or electrons, but we're modifying those things in a way that gets us more bang for our buck, right? More newtons per watt.
All right, look, there's still a discreteness. There's still threshold. The threshold model is that there's still discreteness there, but there's a sub-discrete as well. There's both. You can't just throw out what these energy levels that happen. They still happen. So I don't know how to interact other than what I'm showing you yet with the sub-threshold realm, that it exists. Maybe there's some way to interact with it to understand space better. That's great for you to look at and say, oh, there's this sub-threshold way. Now we know what dark matter is, what dark energy is at all. It was a complete mystery. So I'm giving you a tool of invention to start with. I don't
By
know.
the way,
Maybe
have
I
you
need to do the
someone
cups.
probably asked this, but have you seen the coherent matter wave stuff that Charles Chase was working on?
Who?
Oh, I guess maybe not.
Who again?
Charles Chase, he with the Unlab. No,
No.
Lockheed, he's a Lockheed skunkworks guy. He's come out with a APEC-ish type thing that's once a year called Unlabs. And yeah, Michael, tell them about the coherent matter waves that.
Yeah, so they were using the Aronoff-Bohm effect to adjust the phase of the particles, the matter particles, and they were able to produce what seems like coherent beams of matter by getting all of the phases identical of all the matter particles in a beam of matter particles. And then it behaves as if it's a Bose-Einstein condensate or something, or at least coherent. So they were using some microcavities to interact with plasmas to adjust the Aronoff-Bohm phase.
Yeah.
It was interesting.
Okay. Right. Unlabs. I've heard of Unlabs.
I'm sure this would be relevant to
as
what you're
far as-
researching if you're working with high energy matter particles and gammas. Not as much the gammas, maybe, but maybe there's something there too.
You mentioned the Aronoff-Bohm effect, and I have the equation for it here. And oh, I'm sorry, I lost it. There. And the thing to remember about it is, how is it that a matter wave can work through it without thinking in terms of quantization, by looking at it in terms of thresholding? Is that the E to H ratio is in the scattering equation. And it's the ratio that's conserved. It doesn't have to have a whole charge or a whole action's worth of energy, because the way the equation is structured, it's that the ratio is conserved. So that's how my theory relates to what you just said.
Well, cool. I mean, maybe there's something that you can test using his coherent matter wave concept.
Yeah, I don't know. That would be really difficult. I'd have to read his paper.
Well, I can certainly get you that, or some of his stuff at least. Well, there's some of it's public, so yeah, I'll put it in the chat here in the studio.
Good. I'll study it. Thank you.
So just so we're on the same page, a coherent matter beam would be like you're collimating these alpha particles so that they're all like coming out in bursts together, right?
No,
No,
that's not what I'm doing at all.
I mean, that's what Michael was referring to with Charles Chase.
Oh, maybe, but that's not at all what I'm up to. I'm showing that the emission of an alpha ray is one at a time. It's one atom emission, one helium nuclei burst of matter wave at a time. One atom's worth is emitted at a time, because we know that from the true coincidence test. That's what's so exciting about this. It's not an ensemble that I'm diffracting. It's a one at a time source and then diffracting. So, and that's the test that I do for both light and matter. That's the invention here. Here, to say we see if it's a one at a time source with the true coincidence test. And then take it to a split to show it isn't a particle at all, because it went to 2. You see how different it is? I'm defying the particle property and then seeing what can we apply, how can we apply that first to spectroscopy to understand matter and energy. Later, we'll do practical applications. We're just at like step 1 and 2 now to see spectroscopy with it, to get away from the paradox. And it's like, as soon as you start labeling what goes across space as photons, you're in this. The model, the photon is just a model. It's not anything that you can picture because it diffracts. The model is showing a dualism between the particle property and the wave property. So it's not a photon at all when light goes across space. It's continuous, but we explain the property of it doing clicks and the particle properties with a threshold model. And what I've done in my other lectures and the theory to expand it is to derive the photoelectric effect without the particle model and the Compton effect and the black body equation, and to understand antimatter without particles. There's an inner wave that I use. It's about beats, difference frequencies, that makes the structure that you can use for deriving those equations. I did a derivation that connected the photoelectric effect to the de Broglie equation, a wave equation and a particle equation. Well, nobody connected them, at least not easily. So I connected them with this difference frequency beat model about understanding what is the inner wave, what's going on with this inner wave. Schrodinger talked about beats in his first paper, which was very inspiring to see. He got it right, that the electron is about difference frequencies and beats. And then Compton did a derivation of his scattering effect by bouncing off of these layers of charge. But I converted that derivation into beats, and it made it much easier to understand the Compton effect. So just one step at a time, go back to my other lecture slides to see how I derived those equations to understand the inner wave and how everything is put together. So yeah, I'm just emphasizing the alpha experiment here, but there's a whole lot that I've done theoretically. Let's see, I have some other slides. Maybe I can find a slide of what I'm talking about. Sommerfeld and Dubai, they worked on a loading theory model. Millikan understood the loading theory.
Yeah, Eric, let me put you back in solo layout there. Okay.
Oh,
there we go.
Oh, okay, good. this is my derivation of well, no, this is my critique of the de Broglie equation. Had all kinds of experiments. So I did a critique of it here in this slide. It's in the so the file that's at the top of my website includes all of these other slides that I just put at the end of other material. I just stuck it in there so you could see it. There's a derivation that about the mistakes de Broglie did, and there's another way to derive his equation. And so I use this beat model where the inner wave fits light, where there's an inner Schrodinger wave function that has a difference frequency, and light will fit that. And let's see, this one is good. So it's a very simple concept. So just getting step one right. What's an electron? How does light interact with charge? Just to get that right without wave particle duality. It's right here. It's that the envelope of the inner wave, the Schrodinger wave, fits light. And so there's a factor of 2, like 2 beats per light wave. So you start with the photoelectric effect equation, convert it to 1/2 mv squared, put in this factor of 2, and you crunch them together, and you get the wavelength equation, the de Broglie equation. But now we interpret the wavelength differently in terms of the wavelength of the group, the beat. See, now I relabel the symbols in the de Broglie equation, the velocity of the group, and then what's this little m here doing? You see, that's been the hang up. It looks like it's the mass of a particle. This has been the problem. How do you deal with that? I'll explain how you deal with that. You put the mass on the other side, and you see that it's a ratio, the charge, the action to mass ratio. That's the equation of the experiment. That's the real breakthrough. That slide I showed with all those equations about how the ratios work. That's the big conceptual breakthrough. How do you get to see what's going on without talking about particles? This was a good experiment that somebody else did. Helium focuses. Well, that's really great. But can you still interpret that as a probability wave? And that's where I come in to say it doesn't have to be a probability wave with all the entanglement problems. Also, there was a signature of what went straight through. So this is a big clue. It's that the matter wave, that matter is a soliton, is that it has 2 states. The matter can hold itself together as an atom, but when you start doing these beam and diffraction experiments, it won't hold together anymore. It doesn't all hold together, some of them. And it's different from complementarity. It's that some of the particles will not hold together as particles anymore and will diffract like a wave. It's a soliton, 2-state theory of the matter wave. So the combination of this experiment and my experiment is what makes it all understandable. So this is the first step. Like, what is this guy talking about? Look at the experiments that show the wave effects. If the equation does not have a simple ratio, it's not going to be about waves. It's going to be about how it holds together. So the structure of the equation tells you what's going on. If it's a simple ratio, those equations of the experiment are about how the wave can spread out and transmit its identity of, like, is this an electron? Is it a helium or what? It's the ratios that are conserved. This is the trick. This is how to see through the illusion of everything being quantized. And then, are you going to invent a probability model for it? Well, does the probability model hold up? It does not hold up in my experiments for splitting gamma rays. That's a done deal. I've done that too many different ways, and I haven't seen any way to shoot it down. But so yeah, gamma rays, energy itself. You can go back to Planck's first theory and see how people have misunderstood it, have misrepresented it. I don't know if I have a slide for that, but it's in one of my lectures where you go back to Planck's first theory, and I don't know if I have a slide for that. This is the derivation of the Compton effect. That's important. So that slide is in here. Planck's first theory had his action constant and h nu as an energy in matter. In matter, not in energy, not
actually
in free space.
it makes a lot of sense. The uncertainty associated with matter is much smaller because of its mass energy. So you have the ratio of E to M, and that gives you your uncertainty limit. Like you can use electrons, an electron microscope, to see much smaller features than with an optical microscope, for example.
Yeah, of course. Okay. Now, this is the slide I wanted to do. Just wanted to show. 1900. What did Planck do? Everybody says Planck did energy quantization. It's not true. He did energy in his oscillators. And he says so. The resonators as a vibrational energy. So it's the energy in his resonators are the electrons. It looks like at this time he was talking about quantized energy of vibration in matter, not free space, not like the photon. So people will misquote what did Planck do in 1900. But then he did better in 1911 to say that, it could be a threshold. Let's see. The 1911 thing, I had the slide of it up above. But there's all this history as to how is it that people got into looking at these effects as particles. This is something I mentioned earlier. Schrodinger had it right to understand that light interacts with the beats of this inner wave, his psi wave. So he writes it here. He talks about beats and the periodicity of the beats. And so I embrace this work of Planck and Schrodinger and do a little bit of adjustment to it, and then apply it to the other constants and realize a principle of conserved ratios. And then, see, I had the theory first in 2000. In year 2000, I figured this out. And then knew the experiments with splitting the gamma ray would work. And then went on to splitting the alpha ray. The gamma ray is 2 for 1. Well, there's not going to be a particle experiment to explain that. That defies the very first idea of the principle of the photon. For this particle part, for light, it just doesn't do that. I pointed out how they never did the experiments right to make them think it does that. But this is harder to do with the matter wave, but I've done it. I've done it in several ways, but it could still use more work to show to nail it down that an atomic nuclear wave function does not have to hold itself together to make a full pulse and then another one later at a different time, whatever. These two pulses here out of time, if it happens out of time like that, that's from random emission sources. That's about it showing up as an accidental chance histogram, the time difference histogram. So this is how other people have done this experiment. I'm doing it the same way. I'm looking at the time between the pulses and plotting it. They just see noise. All of quantum mechanics is based on this noise. I'm the one who sees a peak in this histogram to show it's not this. It doesn't go one way or the other. Forgive me for getting overly enthusiastic. I'd like to hear somebody say, "Oh, Eric, maybe I'm doing something wrong." I expect that. That's the name of the game. I'm always looking for how I can do it better and to see how I might be doing something wrong. But all the pieces fit in theory and experiment. So this angle effect, that's something to really work on.
Eric?
Jared, go for it. Oh.
Yeah, Eric, I wanted to ask you a slightly different angle on what you got here. Your setup in your home lab there is really impressive for a home lab, but there's only so much you can do in a home lab. I was wondering if you'd considered, if you had all the resources available to you, or if you had, whatever it took, if there was any way that you would love to see your experiment scaled up or improved if the resources to do so were available, what that might look like.
Well, I'd love it. Of course. I don't have any secrets here. I've been showing this for 20 years. Everyone is free to do whatever they want.
What would a scaled up version look like? Or would there be additional potential mechanisms that you could observe if you had better equipment available?
It wouldn't be that different from what I have to begin with. Really, it's one step at a time. Just to have the angles to control, that's the next step. And I'm about to do it even better. What I might want is better detectors. Like there could be some liquid nitrogen cooled alpha detector. That's what I'd want. That's what would happen in another well-funded lab. But the rest of it would be pretty much like what I'm doing.
What about radiation sources?
Yeah, that's good. The americium, the preparation of the americium is tricky because I'm just using it from smoke detectors, and there's a layer that's protected over it that spreads the spectrum. So I would have them make it without that. So yes, that's what they would do. You'd have a better source and a better detector.
I know that at some DOE labs, right, they have access to much, much stronger radiation sources, and maybe some cooler detection equipment that might be able to have more particles coming off and more particles getting detected, right?
Yeah, well, you could flood the system. I've seen effects where if it's too strong, it gets in the way. You want to see if it gets too strong, the chance rate goes up. So let me try to see. Let's see the chance. The side, if it gets too strong, then the wings of the histogram, of the time difference histogram, this will start to overwhelm and you won't even see the peak. So there's a happy medium of the strength of the source. and I may even have it right to begin with. So I found that with the gamma ray, that could be the case. It floods it out. You want to see this one at a time effect, like you wouldn't use an X-ray beam. There wouldn't be any one at a time. So you have to have a radioisotope that does a decay and emits one at a time. Right. So I know what you're talking about. There's some cases I'd want a stronger source. I have a strong source, but the preparation of the source could be improved. They put a layer over it that spreads the spectrum some, and the detector. I think there's a liquid nitrogen cooled detector for alpha rays. That's the thing I would love to see somebody invest in and do. Right. I'm just doing this at home. It's just myself. It's just whatever I do. I would love to have more people collaborating with me. Or just do it. Just take it and do it. I would help anyone do this in their lab. I've been saying that for 20 years. Go ahead and take it and do it.
Also, Eric, so it sounds like your experimental setup is pretty particular, right? You can't really compare this to maybe any existing setups anywhere where you could use data that people have collected on different experiments that just so happens to overlap in a useful way with yours, right? Like for your thing, it has to be set up this way and no one else is doing it that way.
Well, I tried many different geometries and setups, and you would want to do it my way. You would want to see that the detectors need to be close together, and what kind of beam splitter you use. Nobody is doing this. Nobody is attempting to split particles like a wave because they think it's particles. I'm the only one doing this kind of experiment with splitting the alpha. So no, there's not going to be any other existing setup that you just go into and say, oh, let's try some of Eric's effect. No.
Okay. Well, and so we got about 5 minutes left here, guys, and then we're going to go to Jack. And actually, Jack has provided me with a video that I can put on, and then we'll do Q&A with him after that. So. Yeah, so Eric, did you have some more? You know what? Here, let me put you back in solo layout. You can run through the slides again. Again, the way that you have your camera set up, when you're minimized, it makes those slides pretty hard to read. But it's okay. Yeah, when it's maximized like it is now, it's going to look a little bit different for you than it does for me because you're presenting and I'm viewing the panel.
Oh, all right. Well, I don't know where to go more. I mean, I could just see what I hit on my slides and see if I say something extra.
Yeah, well, and you know, Eric, again, I sent you an email a few minutes ago. Why don't we set up like a Zoom call where you can really just let it all out and run with this thing, you know? Because again, you have so much depth. If you're up for that, you know, let's do a separate call and we could do several hours once you include Q&A and people discussing things and all that. I'm happy to record the whole thing and put it up on the Alt Propulsion channel.
Good. I have the slides here. I have all these extra.
Yeah, I know.
Detail.
Yeah. You have, in terms of depth, you have far more than we can do in like a regular conference session. And that's totally awesome. I mean, I'm not complaining at all. That's like amazing. So it's like, that was why when you started putting the slide deck up, I'm just like, whoa, okay, there's a lot here.
You're looking at 20 years of work.
Yeah, no, it's amazing. It's amazing. Again, it varies, and actually, I'm looking at doing the same thing with Jack later this week. Also, he's kind of hit like he's struck gold with a lot of his research lately, and so he's just generating new content left, right, and center. And it's like, hey, if it's there, so. Okay, well, why don't I do this? So you've been able to kind of run through things. I think we're just about at the top of the hour. So if it's okay,
Let me go.
yeah, let me see. I'm gonna bring everybody back in, and Jack is here. Drew is here. Drew is driving. Okay, I have two for Drew. Guys, put your hands together and give enormous applause to Eric Reiter. Eric, thank you
Thank you.
so much. Thank you
Thank
so
you.
much. Okay. Excuse me. And again, this is one of those days. Okay. So I'm going to take everybody out, and then what I'm going to do, I'll leave Jack in for just a moment. So Jack, sir, I have a video to play for you.
Please, let's do that.
Okay.
Then I'll take questions.
Okay. So let me bring this bad boy up, and let me see if I can do that. StreamYard is always a little weird. I'm going to take these headphones out for a sec because it gets strange. Okay, and they changed. What is that? Nope, wrong button. There we go. Okay, share screen. Perfect.
Right, connections to intelligence.
Yeah,
Right.
but start it at the beginning.
Yeah, there we go.
Right.
Okay, and it's working. Perfect.
Okay. Yeah, just let it run.
Yep, and I will take. I'll take both of us out.
Yeah, okay.
Bohemia, CIA, 1970s. As MIT historian Professor David Kaiser described in his book, How the Hippies Saved Physics, and in the Nova PBS Einstein's Riddle, the Central Intelligence Agency in the early 1970s recruited me and other fringe, hippie, bohemian, eccentric, but credentialed with PhDs from top universities like Fritjof Capra, Nick Herbert, me, others, Fred Allen Wolf, to work on two problems. By the way, I was never a hippie. Nick Herbert, you might say, he qualifies kind of as a hippie, and to some extent Saul Paul Sarag, but I was never a hippie. I was definitely more what Herbert Gold described as a bohemian. Also, even in the sense of the Bohemian Club in San Francisco, Bohemian Grove. Although I'm not a member of the Bohemian Club, I have been to the Grove many times as a guest, a prominent member of the club. So Bohemians are not the same as hippies. Bohemians, we like money, we like fast cars, we like aristocratic women, and etc. So we're not at all hippies. We do not in other words, we're capitalists. We're not communists like the hippies. Okay, all right, continue. So the two problems that the CIA wanted us to work on was how does consciousness emerge from matter, including the paranormal, the UFO, high strangeness, in a good paper by Eric Davis and Jacques Vallée, and also remote viewing. That's the CIA project in the 70s, to which I briefly was associated at the Stanford Research Institute with Hal Puthoff, Russell Targ, and Pat Price, Uri Geller, Ingo Swann, very important. And the second problem, which is more relevant to today's APEC meeting, how do the flying saucers fly? Now, I claim, ladies and gentlemen, to have completely solved qualitatively, conceptually, both of these problems in the sense that the physics explaining them is mainstream and actually relatively elementary, including, in fact, indeed obvious. Once one has the correct general idea that has been hidden in plain sight. Eric Weinstein claims that this physics that I'm talking about was hidden by the US deep state in the early 1950s for reasons of national security. I support Weinstein's general allegation here. In fact, uh, my Cornell professors from the late 1950s, who basically ran the Manhattan Project for Oppenheimer, some of them were at those meetings and were obviously involved. Um, Eric Weinstein has alleged that advanced physics, particularly related to gravitation and anti-gravity, was intentionally suppressed by the US government starting in the 1950s. Yeah, well, that's because, well, first you have to go back to Magenta, at least 1933 in northern Italy, I guess near the Austrian border. Mussolini's people, Marconi was in charge of that, kind of the first Italian Roswell. Marconi was a close friend of my grandfather's distant cousin, Margherita Sarfatti, who, of course, was very close to Benito Mussolini. So I know a little bit about that. And then I know that the CIA was partly created in 1947 because of Roswell and other things. I have a lot of information about that, but I can't. It's not the place to get into those details. And so Eric claims center on the idea that this research, which he believes was part of a golden age of general relativity, was diverted into classified channels for reasons of national security. The evidence for this claim, however, is not substantiated in the mainstream physics community. The key allegations: the Chapel Hill Conference, 1957. Let's see, in 1957, I was already a, I guess, I was I was, let's see, I entered Cornell in September of 1956. So in the spring of 1957, I was still a freshman physics, math, philosophy major at Cornell. And so Weinstein asserts that this academic conference on gravitation was a covert effort by the government to explore anti-gravity and field physics. There is some evidence for that because I was pretty close to Philip Morrison, professor of physics at Cornell at that time. And of course, this is when Morrison, with Cocconi, began to work on the paper on the 21 centimeter hydrogen line as a way of contacting extraterrestrials. So they were definitely into that, although I don't remember any of my professors explicitly talking about anything like Roswell or flying saucers. But all right, connections to intelligence. Weinstein points out the involvement of organizations and individuals with military and intelligence connections, suggesting they act as cutouts to fund and control the research. Yeah, that's definitely true because they did that to me, years later. I mean, very, very explicitly. I mean, basically, I've been funded by them for many years in different ways. And now, alternative physics. Weinstein speculates that this hidden research progressed in secrecy, and etc. Okay, well, that's sort of a main thing topic, which I know a lot about because of my direct involvement, and it's something we can discuss. Okay, let's get to the physics now, and we start with Einstein's 1905 classical theory of space-time, special relativity. Einstein published his special theory of relativity in 1905 before quantum mechanics in its modern form was created in the mid 1920s to early 1930s, primarily by Heisenberg, Schrödinger, de Broglie, Born, and Dirac. The special theory of relativity is really only a vacuum theory. A lot of physicists and physics teachers do not properly understand this. Einstein was concerned with how Alice and Bob, each in what are called special inertial frames of reference, see moving meter sticks and clocks using light signals coming from different points on, say, the meter stick. The meter stick in vacuum can move with acceleration, any arbitrary slower than light way. However, Alice's and Bob's movements, with their detectors, their photon detectors, must have no acceleration whatsoever, no g-force. In fact, Alice and Bob, strictly speaking, must be weightless, totally weightless, no gravity at all. In gravity-free space, outer space, to a good approximation, they each move in straight lines, weightless, no local proper acceleration. And this is not very well understood at all by many people who should know better. The picture on the right is the basic vacuum, what's called conformally invariant vacuum. If there's gravity, it only applies to the Weyl tensor, conformally invariant Weyl tensor vacuum part of the full Riemann-Christoffel curvature tensor in relativity. And we have here, this is the light cone from the point of view of the observer or the detector. Is at the that point, that vertex point where the two cones meet, with time in the vertical direction and space in the horizontal plane direction. And the important point is that this structure is invariant, doesn't change from the points of view of both Alice and Bob, who are moving relative to each other, with what Einstein called that uniformly, no accelerations. The detectors must not accelerate. What they're looking at can accelerate. So it's very important to get this straight. Inertial frame invariance of the vacuum speed of light. Einstein then showed that the coordinate vacuum speed of light, called little c, is invariant. That is the same number for both Alice and Bob, independent of their relative constant velocities, little v. In other words, Alice and Bob cannot be experiencing any g-force. So strictly speaking, for example, if Alice and Bob are fixed to the surface of the Earth, they feel weight. They are actually not in inertial frames. They are in what are called local non-inertial frames. And in that case, strictly speaking, special relativity does not hold. There have to be general relativity corrections, but these corrections are usually very small in practice. So they are ignored and not properly taught in almost every, at least every physics course in America, say in the 1950s, 1960s, that used, say, Halliday and Resnick as the physics book. And incompetent physics teachers continue to confuse the restricted inertial frame invariance of the vacuum coordinate speed of light, little c, with the homogeneity, isotropy, and non-dynamical changes of the static that doesn't change in time as the universe expands, of its numerical value, roughly 300 million meters per second in vacuum. And that's also the same in different directions of our observable universe. So as soon as you hear some pundit say that the speed of light is constant, use your delete button. Do the same if you hear someone say that UFOs use inertial mass reduction, although explaining that will take some time. And here, just to review the foundation of the special relativity, Albert Einstein's theory of special relativity is built on two postulates. The principle of relativity, or actually the principle of special relativity, that the laws of physics are the same for all observers in all inertial, that is, non-accelerating reference frames, and invariance of the vacuum speed of light only in vacuum, not in material. Material is not true anymore. The invariance of the speed of light in a vacuum, little c, is the same for all inertial observers, regardless of their, actually what I call time-like geodesic motions, in the motion of, or of independent of the motion of the light source. Doesn't matter in vacuum. Okay, this is a tricky concept. There's what's called Fresnel drag and things like that, Sagnac effect, and we don't have time to get into that at this moment. Indeed, James Clerk Maxwell in Scotland around 1865 unified light, the little c in the equation below, electricity, the little epsilon zero, the first factor in the denominator on the right-hand side of the equation, and magnetism, the mu zero, what's called the magnetic permeability of the vacuum, which is the second little factor on the right-hand side of the equation. And that first factor I should have said is the electric permittivity of the vacuum. Where these three numbers, the electric permittivity of the vacuum, the magnetic permeability of the vacuum, were measured independently by Faraday, Ampere, and others in the early 19th century. Basically, the electric permittivity of the vacuum has to do with what's called the electric dipole moment of the virtual electron-positron plasma that's inside the quantum vacuum. Of course, Einstein didn't know this, and certainly Maxwell, they didn't know any of this back in the 19th century. This only became clear really around 1947, around the same time, actually, as the Roswell. That's interesting. It's interesting that Richard Feynman did his main papers on all this stuff around the same time of the Roswell crash. That may or may not tie in with what Eric Weinstein's been saying. I never thought of that before. It also ties in with what Phil Corso was saying. It'd be funny if Feynman got some of his great insights from the Roswell crash, but I'm just that's highly speculating. I'm not seriously saying that, but it's something we have to keep in mind. In any case, unknown to Einstein, in 1915, when he introduced his gravity field equations of general relativity, 10 years after the special relativity, we now know from Schwinger, Tominaga, and Feynman's quantum electrodynamics, 1947, again, same as Roswell crash, and creation of the CIA by Alan Dulles and James Jesus Angleton, and the rest of those guys, that the vacuum speed of light is a contingent dynamical physical process that depends upon the structure of the virtual electromagnetic plasma inside what Dirac called the Dirac sea. Now, there are also small corrections from the virtual particles of other species, but the dominant contribution by far is simply the virtual electron-positron plasma, and that's because the charge to mass ratio, the gyroscopic parameter of the electron, is the largest of all the massive elementary particles that we know of, and you can't include neutrino because they don't have any electric charge, although they have weak charge. That's another issue. So there we are. And also, you should see a book by Sir Martin Rees called Just Six Numbers. Explains how the quantum vacuum, is a contingent structure. So that means that although the vacuum speed of light is always going to be invariant for Alice and Bob moving in the vacuum along non-accelerating time-like geodesics, they'll always see the same vacuum speed of light. But what they see, that number may not be 3 times 10 to the 8 meters per second. Somewhere else in the universe at a different time, it could be a different number and still be invariant. See, it's that's why to use the word constant for the vacuum speed of light is no good. It's too vague. It's sloppy thinking, because what they really thinking of is that the vacuum speed of light has to be homogeneous. Has to be the same number everywhere in the universe. That need not be the case. It may be the case, but it need not be the case. It's a purely empirical, not a fundamental issue. And that's the main point that a lot of physicists do not understand. Now, we saw in the previous slides that Einstein's principle of special relativity is that the laws of physics must be themselves invariant of the same mathematical structure, the same form. All the equations, those are called tensor and spinor equations, they must be the same for all inertial frame observers. That is, Alice and Bob are each moving in vacuum. It's got to be in vacuum on what are called zero G-force time-like geodesics, without any G-force and without any what's called local proper acceleration, which is measured by the little accelerometer in your smartphone, in your iPhone. Okay. It can measure that thing, and that's also what's used in inertial navigation in ballistic missiles, the hypersonic missiles, and all that stuff, the ICBMs, unfortunately. So that's the point now. But now, special. What happens if the detector, if Alice and Bob are accelerating? What if they're on what are called off time-like geodesic world lines in the 4-dimensional space-time continuum? So what happens then? Those are called non-inertial frames, and there are corrections. But nevertheless, 10 years later, in 1915, after Einstein did his special principle of relativity, he extended his idea very naturally to the general principle of relativity, that all the laws of physics must have the same invariant mathematical, or it's all actually covariant, of the same algebraic forms, even when the observers, the detectors, Alice and Bob, they could be rotating, they could be accelerating, they could be out in space firing their rockets, so that means that the equations of physics at the fundamental level must be formulated in terms of what is called tensor calculus and spinor calculus. It's a particular kind of mathematics that satisfies the two principles now: the principle of special relativity, in which Alice and Bob cannot move with any kind of G-force, and general relativity, in which Alice and Bob can move arbitrarily. They still can't move faster than light. They always have to move slower than light. All right. And an example of that, now it turns out the vacuum coordinate speed of light, little c, is not invariant under transformations between, say, an inertial frame to a non-inertial frame, or for transformations between two non-inertial frames. In other words, if Alice is not accelerating and Bob is accelerating, when they want to compare their data, when they're both looking at the same external events but they're both detecting, they're looking using photons in vacuum. They have to be moving in vacuum, coming from the object, say the UFO. They're both looking at a UFO, okay? In that case, the speed of light is not the same for them. And a good example of that is what's called the Sagnac effect, in which you just have like a rotating, like a phonograph record, and they have a little photon detectors clamped to the to the to the rotating phonograph record. The speed of light measured at different points on the rotating phonograph record will not be the same. It'll change, and that's called the Sagnac effect. So, and now getting back to this other thing, the contingent structure of the Raxi vacuum. This is a technical point, and I think I'll gloss over this point, except to say that there's something called, something called the Schwinger effect, which is now done with these very high power short pulse lasers. And guess what, guys? The Schwinger effect destroys classical relativity. Because classical relativity, remember I said classical relativity of Einstein, both special and general, by the way, only works in a vacuum. I left out something. The vacuum has to have a special property in order for classical relativity to work. In other words, every physics theory has what's called the limited domain of validity. Einstein's classical theories, both of general relativity, special relativity without gravity, and general relativity with gravity, they have a limited domain of validity, and they do not work if you hit the vacuum very hard with a high power laser in a very short pulse. They don't work because what happens then, you get the Schwinger effect, in which there's so much so much voltage, so to speak, in the laser pulse that it pulls a virtual electron-positron pair out of the vacuum. It creates electron-positron pairs out of the vacuum, real electron-positron pairs. And that means that the phase speed, the wave speed of light in vacuum then depends on its frequency at that high level. And in that case, everything falls apart, and one has to be very, very careful, because there could be unknown phenomena, maybe dangerous phenomena, that happen in that case. So this is just to show the limits of Einstein's classical theory from the quantum mechanical Schwinger effect. Now we come to the key part of UFO or UAP, electrogravimetric engineering physics. This is something that I'm pretty sure the engineers and physicists at Lockheed Martin, at Grumman, or any of the Black projects, they don't understand anything of what I'm about to say. Now, I could be wrong, but we'll see. But this is something that even a lot of physicists don't understand. And this is why everything about the UAPs seems so strange, because they don't understand the basic physics. Relativity inside condensed matter does not work at low energies. It works at high energies, well, as long as they're not too high, of course. It works in the intermediate. You'll see below precisely. Again, to repeat from the last slide, relativity would not work if the classical vacuum at low energy had electromagnetic dispersion. That is, if the far field transverse polarized electromagnetic wave phase speed depended on its frequency. This is, we're assuming that photons have zero rest mass. So photons in what's called the geometrical optics limit, they always move on what in Einstein's classical theory, the geometrical optics limit, they move on null geodesics. Null geodesics means that there's zero proper time. Time stands still for any kind of consciousness that's light-like. In fact, such a consciousness could not exist, but that's another issue. In fact, this is the case for very strong electromagnetic waves, some high-powered lasers at very short pulses, the Schwinger effect. But let's continue now. Condensed matter physicists know this tacitly for the emergent, coarse-grained, long wave, low frequency. That means low energy, effective field quasi-particles, and collective modes confined to the interior of the interacting many-particle system. The condition for relativity to work inside condensed matter is that the interaction energy between the bare particles is small compared to the internal energies of the relevant dynamical processes inside the bare particles. That is, the complex system must be an ideal gas to a good approximation. Now, I think this is pretty new to most of you pundits. You don't understand these things very well. Why UAP, inertial mass reduction, US Navy, Salvatore Pais patent is bad, bogus physics. Of course, the microscopic vacuum relativity corrections continue to hold at shorter wavelengths and higher frequencies up to a point. That is, the binding energies of electrons and atoms and nucleons and nuclear matter still obey special relativities equals mc squared, where m, of course, the inertial mass. That's very important. Remember, there are three kinds of mass in physics. There is the inertial mass, which is Newton's second law, the resistance, how much force you need to get a certain acceleration. That's called inertial mass. There's called the passive gravity mass, which is how a test particle responds to an external gravitational field. By a test particle, it means it has passive receptive mass, but it has zero effective active mass. The active mass is what creates a gravity field. So that when in the equivalence principle, that only applies to test particles, which only have effective passive mass. That is, you can ignore the self-gravity from their actual active mass. You can ignore that relative to the external source mass creating the external gravity field. That's the domain of validity of the equivalence principle. Again, that a lot of people don't understand, who should understand, but they don't. Okay. Now the condition, then there's also the active mass, which I said, which is the self-gravity of the particle, and that's generally ignored in almost all the textbook examples of the applications of general relativity theory. And that's another point. The self-gravity is not well understood. And of course, the whole point of UFOs, these are all internal self-gravity effects, in which you have to be very careful even how to apply relativity. So people, they're totally clueless. The so-called pundits, in my opinion, totally clueless as to what's really going on. Okay, let me continue. The condition for the use of Einstein's equals mc squared inside matter is that the interaction energy between the bare particles is small compared to the binding energy of the isolated systems. This is indeed the case, for example, in the nuclear fission bomb, was it Fat Boy, used in Hiroshima, in which the inertial mass reduction of 0.7 grams, less than 1 gram, out of a total like 64 kilograms of the bomb itself, of the fissionable material in the bomb. So this is a very tiny fraction released in about a microsecond, produced more than 10,000 tons of TNT. This is why any claim by crackpots that UFOs reduce their inertial mass to zero is idiotic rubbish. I repeat, it's idiotic rubbish. Throw those bums off the stage if you hear them say that. Furthermore, even if that happened, it would not explain the motion of UFOs. Any object with zero inertial mass is in the geometric optics particle limit of small wave diffraction moves along a null geodesic. That's along the light cone that I showed before. In addition, a zero inertial mass electrically charged particle is not possible because the electric charge itself creates inertial mass. Now, I'm just a quick quote from Elon Musk's Super Grok, which says, Jack Sarfatti's text provides a concise and provocative overview of how special and general relativity interface with quantum electrodynamics, QED, and condensed matter physics, while sharply critiquing pseudoscientific claims about UFO propulsion. As a physicist known for his work on extensions to general relativity involving torsion fields and potential applications to advanced propulsion, Sarfatti draws on established principles to argue against simplistic ideas like zero inertial mass. I'll break down the key points and offer commentary highlighting accuracies, nuances, and implications. And at this point, I'm going to stop this particular APEC presentation. I include, you could get it offline, the rest of what Elon Musk Super Grok says about this issue. And this is a good point to stop and to get into more details on how the UFOs actually work in a separate lecture. We can't do, even God needed 6 days to create the universe. And I can't do everything that should be done in the space of 1 hour. I may have also already gone over the hour.
Okay, Jack, we're here. There we go. Okay, so let me add everybody in. We'll do Q&A. Yeah, so I think we're good there. And I have Eric up. Okay, so guys, before anything else, let's put our hands together and give an enormous applause to Mr. Sarfatti. Okay, yep, and Eric took down his thing. And let me unmute Jack.
Unmute. Okay.
Okay.
Can you hear me
I'll
now?
bring
I'm
Drew in, but
unmuted.
no fighting. Okay. We did it. We're getting there. So my new mic is picking up everything, huh? Okay. I'll see if I can fix that.
Okay. Any questions on what I said?
You have a ton of detail there. So you generate a lot of this working with Grok, right?
Yeah. Yeah.
Well,
But what
that's
I'm doing here, this is only like 10%, right? Because I'm just trying to introduce the foundations of relativity. That, by the way, a lot of physics teachers don't understand it very well. You see, you can do the mathematics, you can solve a bunch of problems. The textbooks they only have a superficial understanding of it. You can do the mathematics, the formal mathematics. You do quite a bit of physics with just the formal mathematics without understanding the physical meaning of what these symbols really mean. And this is especially a problem with theoretical physicists. Engineers, just the opposite. The engineers know how to do equipment, but they don't understand the theory very well. So there's like a cultural, there's a gap. There's a cultural gap. In any case, are there any questions? No questions?
Well, yeah, Joel, go for it, sir.
So thank you very much for the presentation. So you already went quite further in the open mic session last time, right? So I really enjoyed the presentation. I think it's very good to set a strong foundation on general relativity, but I would have wished for you to already go deeper into your equations and what you're actually doing right now.
Yeah, well, I can't because the audience isn't ready for it. They don't, like in as you know from a university, you have to have prerequisites. And what I found is that people haven't a clue about what I'm talking about because they couldn't pass the courses in physics and math at the colleges and universities. So the point is, maybe you can understand the more advanced, but the people, and it's not just the people here. I'm not just talking about the live people. I'm talking about there'd be hundreds, maybe thousands of people on the internet, on YouTube, watching all this stuff, right? Because I'm promoting. I have 14,500 followers on Twitter, on X.com. I have almost 40,000 followers on Academia Edu. I got another like 12, 15,000 followers on Facebook and LinkedIn, and there's also Truth Social. There'll be, and there'll be a lot of people watching this, and they can't understand anything I'm talking about properly. In fact, the real problem is Louis Elizondo can't understand it. Right? None of them. Jesse Michaels, all these people, all the guys talking about it. Joe Rogan. Do you think they understand any of this? Do you think the Congress people understand it? Do you think, well, what is Tim Burchett? And then we have, people like the Admiral, the Navy Admiral Tim Gaudier. Everything he says is correct, by the way. They have the evidence, but he doesn't know. He knows oceanography. He knows certain things. He's very good at what he knows, but he doesn't understand any of this stuff, basically. And so it all looks strange to them. And and this is a real problem. But let me tell you one thing: there are people who do understand it, but they're in Moscow. They're in Moscow. I was invited to. They wanted me to come to Moscow 2 years ago. Moscow State, right? The people in Moscow, they understand it. Beijing,
well, I think some of the people who do understand parts of it and try to understand it all are also here, are also part of the APEC community. So yes, I really like your presentation, and it's a good setting, right? It's a good basic step. And I really would like to see the next steps, and I actually would have loved to discuss some of the deep ideas that you have been putting out in the last weeks. Maybe we can do so today. Maybe we'll go. Okay, maybe I will just go. Like, one of your central ideas is this x transpose x much greater than 1, right? So this
say that
idea.
Again. I didn't hear. Say it again. Repeat that.
The capital X transposed and x much greater than 1. That is like one of your central ideas. So the resonance regime, right?
Yeah. Wait. Okay. Yeah. But be more specific. I'm not sure. I'd have to see. Can you share the screen? Can you draw what you're talking about? He can. Tim, can he share the screen?
He can do a screen share, but I don't think he can do annotations. That would be Zoom. StreamYard is.
Yeah,
I
don't have an iPad like you got usually, but
I don't know what X is here. I don't remember saying anything about X. I remember saying like there's two coupling coefficients. There's K1 and K2. Are you talking about that? There is the.
No.
Oh, you're talking about a resonance?
Yeah, the resonance regimes, right?
Yeah, but the resonance in what? Now there's the electromagnetic resonance is like the index of refraction as a resonance, right? Is that what you're talking about? But without the equations,
that is exactly the problem. I would have loved to see a presentation with the equations and then
go
you can't do that.
You can't do that in an hour. This requires 20 lectures, right? Like Lenny Susskind and his Stanford lectures on quantum relativity. It's a course. There's a reason why courses take a semester.
Yes.
You can't.
So, Jack,
what?
Well, so one thing I might be able to assist with is like putting in. This isn't a great description, but putting in place kind of a ledge for your material. And I think you're absolutely right. One of the problems is, I mean, you are a theoretical physicist with a PhD and decades of experience in this. And this is an area that is very niche to begin with. So you have niche experience, right? And so one of the things that I have been doing lately is I'm using a couple of different AI tools to create summaries of podcasts and interviews. And in fact, while this presentation was playing, because it was pre-recorded, I actually created a summary of it. Now, it's still very raw. I can put it up if you'd like, but
let's see.
Yeah. Okay. Maybe. Well, I'll show you. Yeah. Again, it's not magic, but unless
somebody has some urgent question, but if not, let's see it.
Yeah. Well, I'll do a share really quick, and you can at least see kind of what I'm doing with this. And again, my hope is not here. Let me see if I can. Okay. Share screen to transcript editor. There we go. Okay, so this is the lecture that you just delivered,
Okay,
And this is the raw transcript of it. It's very raw, right? It's just
Send it because I can't. It's too small. Can you make it bigger?
I can do that. That might help a little bit.
Yeah. And by the way, I have a lot of things on my x.com. I have a lot of Grok summaries like this too. So
yes, exactly. My hope is by creating summaries like this, there's no math in this. But my hope is that this will help open it up for people.
Yeah, absolutely. Do me a favor, send me that so I can link it. I'll link it on my x.com. Yeah, I have like 50,000, 60,000 followers all. So I'll put it out there.
And then the other thing I've been doing, again, I've been putting these up on the Alt Propulsion and the UFO Rev websites, and I expanded all of those bios too. So what I'm trying to do is put our best foot forward as a community and make everyone look as good and be taken as seriously as possible.
Okay, now here's a question. There was a question from Brendan McNamara. I saw.
Yeah, Brendan's in here. Where's Brendan at?
Let me just see. Let me just read it. Love to hear Sarfatti. How does fight? What? It's gone. I can't read it. It disappeared. It went up and then it disappeared before I could read it. McNamara's thing.
It's scrolling up. Oh, there it is. Jack mentioned that objects such as photons moving at light speed have a null geodesic. What does he think happens to consciousness in a craft projecting a warp field?
Well, those are two separate. It's apples and oranges. So there's no connection between the two parts of the question.
Yeah.
There's zero consciousness at light speed because without time flowing, right? There's no proper time. I mean, your consciousness requires the time duration, right? Quality. We experience things in time. So if the proper time is zero, and also you can't have any mass, you can't have any electric charges. There's a whole contradiction. You can't have ordinary mass. We can't exist at light speed. Even both classically and quantum mechanically. So. But there was a question he asked before that disappeared. I don't know.
I'm not sure.
Yeah, I was the one that accidentally bumped his off the screen. If I can ask you a question, Jack. I wanted to ask you about the Sarfatti factor. Specifically, its value seems as though it's derived from like the most ideal conditions of plasma possible, but those values they seem really, really high. Like the plasma has to be super strong, B field that has to be very low frequency. I was just wondering, what's the most feasible value that we could achieve in a plasma, and does that attain the proper Sarfatti factor to be useful?
Okay, good question. Now, that particular work was not me. That was Michael G. Anderson at the Lawrence Livermore Nuclear Weapons Lab, who did that. He didn't even tell me about it. He cited my work. He uses my idea. And he also has some other, additional stuff to it. He uses the idea. And he has a actual proposal for a machine, right? That where this is called the S factor is like, it's a dimensionless number. It's actually a complex number, but that's another issue. But right now, just think of it as a real number. And in his machine, he thinks he can attain an S of 10 to the 32, I think it is, 10 to 32. That corresponds to an index of refraction of 10 to the 8, because the S factor is basically the fourth power of the index of refraction, roughly speaking. So that would mean 10 to the 8. That would mean, say, in the case, the effective speed of light, which is normally 10 to the 8 meters a second, in the plasma, it's down to 1 meter per second. Down to 1 meter per second. Okay. Now, and then he says that with that he can make a little warp bubble. He says the plasma will form a warp bubble of about, and these are not my count. This is, the government. This is, this is Ed Teller's lab. This was Ed Teller's lab, right? They're the weapons place, right? And they say there'll be a little vacuum bubble about I think it's 1/10 millionth of a cubic meter. And on the surface of this bubble, the effective G field is like 16,000 Earth G. Yeah, okay. Then they'll see stuff. They claim that, but they need $250 million to do the experiment. All right, and also, but apparently, the machine, they have other uses for it. A $250 million machine, 30 feet high and 60 feet. It's a giant Frankenstein kind of machine. But they're going to use it for nuclear weapons simulation. They use all kinds of things. And I guess it's for fusion. They're studying fusion or whatever. I don't fully understand. In any case, Mike Anderson asked me to sign an NDA, to help to work on a thing, but I didn't. I said thanks, but no thanks. Use my stuff if you like it, because I don't want to be restricted by any NDA. I don't need to know, what they're doing, the details. I don't care about that. But the general point of your question is very important, because basically this S idea, the idea that the active mass, it's very simple. The basic idea is that the active mass for self-gravity, if you have a chunk of mass, okay, and if you weigh it, when you weigh the mass on a scale, you're measuring, the weight measures passive gravity mass, doesn't measure active mass, okay? And what I'm saying is I have reasons for saying what I'm saying. What I'm saying is that basically what you have to do, and I'm oversimplifying to some extent, basically you have to take your passive mass and multiply it by the square of the index of refraction of the electromagnetic field, at that mass. Now, if you're doing things at frequencies, you have to do the Fourier transform. So basically what you have to do, there's a generalization of the index of refraction. It's called the electromagnetic susceptibility, and it depends on both frequency and wave vector, and what's called the near field, your off mass shell. In quantum field theory, your off mass shell. You're off, being ordinary light waves, the radiation far field, those correspond to the poles of, say, of the Feynman propagator in the complex energy plane. Then we're off the pole. So it gets pretty complicated. And but the problem, here's the basic problem. See, the problem that you're hitting on. Now, one thing I can say is that the effect that I'm predicting here can be measured in the lab very cheaply in a Cavendish experiment. But it's weak. It's still going to be too weak to explain the UFOs. Basically, it's too weak.
How has that experiment happened already with the water?
Well, I don't know. Okay, here, that's a good question. I wish I knew, because people do things they don't tell me, right? Okay, all I know is this. That working with Elon Musk's Grok, I guess 2 months ago, is it now? Elon Musk Grok figured out a very cheap, $20,000 experiment can be done. It could be done in high school labs. It could be done in any college, community colleges. Anybody could do it, right? And Elon Musk he did everything. Every number, what you need, this and that. Everything is figured out. There's no. It's like fill in the dot. It's like painting. These little things where everything is outlined. You just put in the colors. You just do the experiment. It's a simple. I mean, Cavendish could have done it in 1798. He could have done it. All you do is you take a big chunk of ice, 2 chunks of ice, and let it naturally melt. Well, you have to have it in a container, of course, and you let the ice melt, and you'll see if I'm correct, you'll see the torsion balance swing according to Newton's laws. It's a simple little, it's all there. It's all spelled out. And that'll test the equation, because the nice thing is that when ice melts, the effective index of refraction goes from say a pure number of 100 down to 80. So it's a 20% effect. And if the if the active mass of the ice melting to water is proportional to the square of, so to speak, of the index of refraction of the ice, and as the ice melts to water, that index changes, you're going to see a change in, the relative angle, in the horizontal plane, the torsion, the angular separation between the big masses and the small masses. Cavendish. So Cavendish could have actually done this experiment. He could have done it, 1798. Wait, let me finish. Let me finish. I haven't finished the what you need to know. So when Grok did this, I posted it on x.com about 2 months ago, and in the first 24 hours, there were 20,000 views in 24 hours, all over the world. You can see Russia, China, everywhere, Germany, all over the world, Australia. China. Okay, so now the thing is this. If the experiment works, as I say, it's proof of concept of electrogravitic, basically. But the effect is still going to be too weak. That's not what UFOs are doing. UFOs are doing something like that, but not that particular. They're not. So here's the thing. Let me give you a little background here. This is what I think, Eric Weinstein, when he says the guys, my physics professors, other guys back in the 50s, that they hid this stuff, I think Eric is correct. They hid it in plain sight. So I think I think John Wheeler and Feynman and, DeWitt, all these guys, they probably understood everything I'm telling you, because it's not, it's kind of obvious, really. I mean, the reason people don't see it is because in the way they teach physics today, and I think it's done deliberately, just look in text, and think of your own physics courses, okay? If you took general relativity, did you ever learn that the coupling depends on the speed of light, or did they just, right away, they just take what are called natural units? They hide them. The C equal 1, H equal 1, E equal 1, G equal 1, like everything makes the 1. So they're hiding the engineering part of it because they don't want you to realize that. Okay. I mean, were you taught, anybody who took any physics, were you taught by your teachers that the coupling of matter to gravity depends on electromagnetism? The only thing was Newton's gravity constant, right? Just big G. Did you agree?
There's natural units, and you're right. That's true.
They don't teach it in undergrad. It's at least at the grad level or higher.
Yeah, and I mean it's there. They can't hide it totally, because it's, it's physics. But it's what's called misdirection. It's mind control. It's what the CIA, it's what also that's another thing. It's all propaganda. It's all controlling the narrative. They're still doing it. Go ahead,
Jack. I'd ask this in email, but is there a good day, maybe like in the evening next week, to set up a Zoom to let, again, like we were talking about for Eric, just to let you roll, because you've got so much.
We could shoot for. He wants to do Tuesday, because Monday is a holiday, right? If you want to do Tuesday, we can.
Okay.
Okay, but getting back to the issue. So the question was, did anybody do the experiment? They may have done it, but let's put it this way. If anybody in the military or the intelligence community does it, they're going to keep it secret. They don't want people to know it.
Yeah, I mean, they want the advantage. One other question. Have you seen Chance Glenn's research? He was doing a similar... so they have that basically giant Z-pinch they're making in the national labs to try and get this effect.
Okay, here, slow down, speak slower. Repeat what you just said. I know who Chance Glenn is.
Yeah, so have you seen the spark gap experiment?
What is he doing?
Well, he was doing a smaller scale experiment similar to the experiment you discussed to try and get a very large S factor. So he did a much smaller.
What's his experiment? Tell me what is his experiment?
Well, he was just testing for the same sort of S factor in an ordinary spark gap.
I don't understand. I don't understand how it connects. I'm talking about a Cavendish experiment. You're talking about a.
Well, no, this is before
Yeah.
before the Cavendish experiment. You mentioned that they were proposing an experiment for a multi-million-dollar machine, which was if I recall correctly, it was just
okay,
right. So.
Okay. Wait. So here's a plasma.
So Chance Glenn just saw a similar effect to what was predicted in the Z-pinch in a much smaller spark gap recently.
Okay. Hey, fix your camera. You can't see all your face. Your face. Look at your camera. Okay, that's better. Okay. All right. Do me a favor. Send me his experiment. I haven't looked at his latest. I thought he was doing stuff. I thought he was doing stuff like Sonny, and that guy from Connecticut with light. With interferometers.
That didn't pan out. So he was like, he realized he needed much higher energy levels, which is
it's too weak. It's too weak.
Yeah. So he went to the spark gap, and it worked.
Okay. All right. Okay. Yeah. Well. Okay. Yeah. I'd like to see that. Yeah. So he's doing kind of a poor man's version of what Lawrence Livermore is. What you say?
Well, what the interesting thing is here is if an ordinary spark gap will do it, maybe it's a lot more engineerable than his machine. But of course,
it's still going to be. It's still going to be too small.
Fusion testing.
Okay. Let me tell you now what I do know. Okay. In a general, I got to be careful because we're getting patents. What I do know is this. Generally, the fact that the Einstein coupling is so weak that it's 10 to the minus 43 reciprocal newtons of force in MKS. Yeah, the Einstein coupling. That's what it is. And it's very weak. So that means space-time is very stiff. It takes a tremendous amount of stress energy density to really manipulate the gravity field, right? To do anything. And even if you can, do this S field thing, it still seems that it'll be okay. Even a Chance lens thing, even it gets an effect, it's going to be very weak. You can't lift a craft. You can't propel a 3,500 pound flying saucer with that. Okay, and you can't do even the Lawrence Livermore. Even if they got their thing to work. We happen to know that these flying saucers do not have 30 by 60 foot fusion reactors inside them. In fact, they're empty. They're pretty much empty. I happen to know about some of this stuff. I happen to have inside information on some of this, what these actual real craft are, and they're pretty much empty inside. So everything's everything's done in the thin shell fuselage, So there's no apparent propulsion. Now I'm talking about the advanced ones. There may be earlier ones, what I call ARVs, the alien reproduction. Maybe some early ones with, like the Bell, like this alleged Nazi Bell, all that, where they sort of have, stuff. But I have my doubts about that.
Yeah.
But the point I'm trying to get to, I digress too much there. The point I'm trying to get to is that there's an additional effect, which I didn't know until about a year or so ago, maybe 2 years, because of meeting this kid, this ex-Marine named Juan Faria. Met him in Italy, and he's an entrepreneur in Dallas, Texas. So he set up a company called Texas Space in Dallas. A defense, he's trying to get defense. Yeah, he's a Marine and he can get all this stuff. And he's already in the cybersecurity business. And I connected him with Ray Chow. And Ray Chow is a retired. He's sort of my age. We knew each other in the 60s. We sort of briefly collaborated on some laser stuff when I was a young assistant professor at San Diego State. He was a young professor at Berkeley. In any case, Ray has been thinking about how to connect electromagnetism with gravity. He's got all kinds of experiments, all kinds of ideas, and one of his ideas, which I didn't know about what's called the electron spin. And I can't go into detail on it, but it turns out, and Ray, I actually went beyond where Ray was at, because Ray was trying to transduce like gravity waves coming in and produces an electromagnetic signal going out using spinning electrons in a quantum entangled, using like 4 quantum entangled electron spins. And he thinks in a certain material, a ferroelectric material, he thinks that effect would be big enough to get an effect out. And so for passive detection, it seems what his argument seems to work, but there's a problem about whether you can reverse it, whether you can generate a gravitational field using this electron spin. It's a quantum mechanical spin effect. And if you go on my, you'll see if you go on my x.com and look at the technical, forget the political stuff, but just look at the physics stuff I post. Where the Grok, you can see what Grok says about all these things. Basically, there's a extension of general relativity. Now we're getting into what Joel was asking. There's an extension of general relativity called Poincare gauge theory. Okay, and when you extend that, you get additional terms. What is the torsion field? The electron, the quantum mechanical spin. In other words, if you have material, and if the excitations in the material have a net spin on them, they will generate inside the material. They'll generate what's called the torsion field, and that torsion field comes in at least 2 forms. Ordinary gravity, curvature. Ordinary gravity from Einstein, it comes from curvature, and curvature of space-time is, and that comes from stress energy. The stress energy density of matter creates the curvature through something called the Levi-Civita connection, so there's that. But then you get this additional thing, which is okay. So the curvature effect in general relativity, when it's quantized, it's a spin 2 field, a spin 2 tensor field. The torsion gives you a spin 2, but an additional spin 2, but also gives you a vector field, spin 1 gravity. And spin 1 gravity is well known to have anti-gravity. In fact, that's it's just like electromagnetism. There's like positive and negative spin 1 vector torsion field. You get anti-gravity easily that way. But here's the big thing. The big thing is that the quantum mechanical coupling of what's called the spin density tensor inside the material, inside the metamaterial, if you design the right kind of metamaterial so that it has spinning excitations in it, that's going to create okay, it's going to create a much stronger gravity. In the case of spinning electrons, just let me finish. Don't interrupt me. I'm giving you gold now. So don't interrupt.
I know. I'm just
okay. All right, just hold it. Spinning electrons. Okay, the effective coupling for Einstein was 10 to the minus 43 reciprocal newtons. For spinning electrons, it's 1 reciprocal newton. 43 powers of 10 stronger. For nuclear spins, it's about 1 million times less. Using kind of Ray Chow's, using an idea that I got from Ray Chow.
So,
right?
Tim, I know you want to.
So the problem is, let me. I'm not done. I'll tell you when to talk. Let me finish. The problem is, it's too strong in many cases. It's so strong that it makes nuclear bombs look like firecrackers. So you got to be very careful. It's be very dangerous stuff. This results now. So that's where we're at. Now, of course, Moscow is very aware of this. People in Russia are very aware of this. As far as
there's been Russian torsion research since the 70s or something.
Yeah,
right?
well, we had those. We had back 20 years ago. That's the other thing. We had Joe Furman. We had ISSOs. It was Bernie Hayes, Hal Puthoff.
Guys, let's. If it's okay, let's. Yeah. So Jack, I emailed you about Tuesday let's do again. This is
All
you
right.
got to go long form, man. You got to go long form because
All right.
you have too much good stuff.
I want to
But
ask
so-
about Kai and the
No.
metamaterials, and yeah, there might be a longer form thing.
On
So-
Tuesday, yeah.
Yeah.
And maybe we should also do more than one, right, Jack? If you want to do a real lecture series on this
No, it's
topic,
got to be a
it would
series.
be.
There's got to be a series. There's at least like a semester course here.
Yeah, I'm up for
Yeah, you
that.
can't,
I'm up for that. But so
We're totally down for that, Jack. Yes.
Yeah.
for right now, let's put our hands together and give Jack
Right.
another giant applause.
Oh yeah, you want to?
And I'm sorry for cutting things short, but we're there and we're
Yeah, that's
agreeing.
fine. That's
Curtis
good.
is
That's
with
good.
us. David is here. So let me do that. Let me take everybody out.
Okay.
Except there's
I'm ready.
Curtis. Okay. And let me see. Oh, and there's okay. I'll take Jared out too. So, guys, I think you were the only two people who were able to join. So I wanted to do a tribute to Jim Woodward, who passed. And David, you had a few words that you wanted to say.
I did.
Did you want to? Yeah, and you've been here for a couple hours, sir. Can I spot?
Before we start, Chris wanted to join as well, so I think he's waiting for the email for the StreamYard link. If you want to send him that.
Yes. Or do you think you could send it to him?
Maybe. And I know Michelle was having technical difficulties, so
yeah.
Maybe if David, you want to start, I'll send a.
Sure, you bet.
Yeah, and then let me spotlight David, and then we'll. Okay, take it away, sir.
Okay, thank you. Yeah, good evening. This is David Jenkins, UC Davis Electrical Engineering. I wanted to first mention that Jim was a cancer survivor. He had severely limited movement. In order for him to walk, he had to use heavy canes and just kind of drag himself around. So the fact that he accomplished anything is a monument to his passion that drove him to accomplishment and greatly exceeded his doctor's expectations of his survival. So he lived many years past when the doctors thought he would be survive. So I'm a classically educated EE, so anything out of the ordinary is difficult to foresee. And one thing I like to say is my college roommate became a structural engineer. He could see the results of his designs. I have never seen an electron, but I can know how to make them move. My interest began in about 1998 when Jean-Louis Nodin claimed excess energy in an experiment. Of course, to me, that was couldn't believe it. Anyway, he had duplicated what was Tom Bearden's motionless electromagnetic generator, the MEG. So I became interested in alternative science and was on many such groups, typically hosted by Yahoo at the time. So during one of these events, someone mentioned the Woodward effect, and I did some research. And Jim had written a paper on his original research, included some simple mathematical equations to support his results. And he had received a patent called the Method for Transiently Altering the Mass of Objects to Facilitate Their Transport or Change Their Stationary Apparent Weights. This was his transient mass beginning. And the concept was very simple. You alter the energy density of a material quickly. So what he was doing was he'd charge a capacitor, and then by Einstein's equation, mass is going to increase when the energy increases. And so if you do that quickly enough, you get a very large change in energy density. Now what you do is when the capacitor is charged, you push it with a piezoelectric transducer. You discharge the capacitor and you pull it back to its original location. Now the force required to push it when it's charged is larger because the mass is larger than the force required to bring it back when the mass is left. Seemed perfectly reasonable to me, so I tried to duplicate it. Unfortunately, Jim used second-hand components which were difficult to obtain. So I theorized what combination of capacitors and piezoelectric transducer would give the best similar performance to Jim's experiment. I built a test stand with a balance beam on a razor blade with a laser light shining on a front surface mirror, which light would travel about 2 meters, providing a sensitive indication of any kind of mass change. I had a null result, which told me I didn't understand what was going on. I needed far better tools to assemble the test article and measure its response. So that got put on this shelf. The result should have been millinewtons of force, but it seemed to be a null result to me. So Jim wrote and published a paper in 2004 entitled Flux Capacitors and the Origin of Inertia, which further detailed the general relativity interpretation of what is occurring. At some point, Jim had an electrical issue, and I contacted him to offer support. I think he had something mundane, like he'd built a transformer to match the output of his audio amplifier to his piezoelectric crystal, and was wondering, did he do the right thing? So I measured out, found out he'd done a very good job. And thus began my interaction with Jim and this small group forming around him. So Dr. Hal Fern put together a workshop at Estes Park in 2016, inviting speakers such as John Kramer from the University of Washington, George Hathaway from Canada, Greg Mahalik from Aerospace, and John Brandenburg, whom we've heard occasionally. It was great fun discussing leading edge thoughts with these guys about physics. So Jim was using a high power audio amplifier to drive his piezoelectric transducer, which dissipates all the energy in the system. It's completely lossy. So I knew there was a much more efficient way of doing that to conserve the energy circulating in the system. So I designed and built a prototype which could be the basis of a lightweight, efficient driver for space operation. It would have, it's probably about 90 to 95% efficient. So we had a couple more group meetings, and Jim was always the gracious host. He always had a house on the mountainside next to the YMCA camp at Estes Park, and I would help him go out into the stores because he couldn't carry anything, and we would select food and refreshments because he loved his guests to feel comfortable at his meetings, which he invited to after our normal meetings. In our last meeting at Estes Park, Jim drove me into the Rocky Mountain National Park, which he loved. He had an annual pass to the park, and he'd stop often to allow me to take pictures of various areas. He loved the outdoors as much as he loved the mysteries of the universe. I helped him buy refreshments, as I said. Thankfully, almost Dr. Curtis Horn came along to greatly help Jim with the mounting and similar physical details of the current experimental research, which has made great advancements. That and the air slide replication made by Michelle Broyles provided interesting results. Jim was an inspiration to those who toil in the shadows with strong ideas and the will to implement them. Jim never complained about his infirmities. Not once did I ever hear him complain. He just kept pushing himself and asking a bit of assistance from others. So let's see. So I want to just say that Jim is a testimony to you can do whatever you want to do if you're willing to make the effort to go ahead with it. And that's my tribute to Jim. He was a great man to be with and know.
Okay, and then David, thank you so much. So why don't we hold? We will do an applause. We absolutely should. If it's okay, let me go to Curtis, and then Curtis, you had a few words you wanted to say also.
Sure. Yeah. So actually, I'll show this. This is one of the magnetic rails we were working on, the linear system. So actually, let me try to unblur real quick. Get rid of the blurring there. There we go. So as you can see here, it's a magnetic levitation. Actually, it's only magnetized inside, and you can see there's a couple of bearings, but the bearings are basically guide bearings. So it's very sensitive to motion. So this was what we were working on, and actually at the end there, the week before Jim was in the hospital. He was in the hospital for about a week. He had picked this up from the machinist at the campus. There's a second one that Jim has. So I had gotten two of these. They're about 1 kilogram, and they're a company called Ironlev that makes these. And so they can be positioned either way, this way or this way. What we were planning on doing was, I'm still going to do it, is run the experiment in a way where it is the device will be hanging. And so if it moves, it's a linear motion. So there's no more of this torsion balance, which is basically kind of goes back and forth, and you're at the end, and it has that kind of thing. So in terms of the experiment, I'll start off with that. That was Jim's passion. It took a while to convince him that, hey, let's try this. That's one of the things that, like David said, Jim had his challenges, and I was able to work with him full time for quite a while I had to go back to work last year, but until then, I was working with them pretty much full time. And, even then it would take quite a while to convince him to change things. Jim had built up over decades a specific way of doing the experiment, and had taken some steps forward, some steps back. And when we did do a change that was a positive thing, he would jump on it and keep it. But he was very hesitant to change certain things that he was concerned with null the effect, right? So what I'd like to do next is basically talk about who Jim was, why I was working with him, who I am. So I was a physics student at basically I went to Fullerton College. From there, I was kind of recruited at Rensselaer, and so I went to Rensselaer. After going to Rensselaer, I came back to here in Southern California, and I was looking for graduate schools. And one of the graduate schools I looked at, of course, was Cal State Fullerton. And I was interested in there was a couple of people there, and I was always interested. Mainly, the interest I had was general relativity and unification in terms of what Einstein was doing, right? That was the program that I was interested in. And the problems that Einstein was trying to figure out, like inertia, things like that are, still questions for a lot of people, most everyone in the planet. So Jim was one of the few that were working on solutions to this. There was another fellow whose theories that I learned while I was at Rensselaer, Mendel Sachs. He was a professor at SUNY Buffalo, and upstate New York as well. Western New York, and I was considering going there to grad school, but I just couldn't take the weather. So I came back to Southern California. I was going to work with Jim, but I ended up not going to Cal State Fullerton. I ended up doing other things for a while, and I eventually moved to San Diego. So that my first meeting with Jim was like in the late 90s, I would say. I don't remember exactly what year. So I went and saw his lab. Some of the pictures that are in his book, I recognized some of that stuff that was, I think at the time he was doing some kind of a rotational type experiment. And I was really keen on working with him and solving inertia, because that's one of the big mysteries, right? Supposedly mysteries that we have. So after that, I ended up coming back to Fullerton, or back to Southern California, working as a control systems engineer. And I was able to, had been wanting to do a master's in physics while working. So eventually I was able to do that at Cal State Fullerton. I attributed it to them building parking structures, because then I could get to class on time. So it took a few years, but I eventually went there. This was around 2006, I think. 2006, 5, 6, 7. I ended up from there. When I was there, I did talk to Jim. I did consider working with him. My grad advisor was Hal, and Hal talked me out of working with Jim because Hal knew that I wanted to go to a PhD program. So because of that, I worked with Hal, right? And Hal at the time basically convinced me. Hal had gone. The head of the department had gone to a conference. He was a condensed matter physicist, and he came back and said that there was a challenge to write a paper on the physics of football. Why does the football, when you have a perfect throw, why does the axis of the football follow the path, right? Why does that motion happen? So Hal came to me one day and said, "That's going to be your thesis." I'm like, I was there to study, relativity, unification, other things, but anyway, so that's what Hal ended up having me do. And I ended up getting in several places. I had the opportunity to work at CERN, some other places where there were national labs that were interesting work. But where I ended up going was UC Merced. And the reason why I went to UC Merced was to work with Roland Winston, who was he used to be the head of the department at University of Chicago. He was basically a particle physicist, and also he did a lot of optics. So I was really interested in working with him. And that's where I ended up going. So once I went there, I found out I came to visit Hal a couple years later, and I found out Hal was working with Jim, and so I was like, Hal, you know, you said not to work with him. Here you are working with Jim. So what I would do is I'd go talk to Hal. Basically, you know, I'd go visit Hal once or twice a year and talk to Hal about the experiment, what they were doing, give them suggestions, you know, that kind of thing. So eventually, and this was about 2020, 2021, you know, they had gotten NIAC awards, the phase 1 and the phase 2, and they were making progress. So in 2021, I knew that they were, I think it was 2021, that we were going to apply in 2022. So I talked to Hal and said, hey, I want to join the program. I'm going to leave work and come and work with you guys because in NIAC phase 3, you're going to need serious effort, right? So I have some engineering chops. I know the physics, you know, that's what I wanted to do. So from October of 2021, I started working with them as much as possible. And it was shortly, one of the things that was happening at the time is they were doing the experiment with the pendulum in the air. And that was something that I was not comfortable with. And so, you know, being new, you know, I had known Jim over the years, but really we're more acquaintances. He probably didn't remember my visits. But, you know, I did, you know, Hal was telling me, okay, go ahead and speak up. And so I did mention to Jim, hey, I'm uncomfortable with this in the air. You know, let's test it. So one day Jim went and put some baffles, and sure enough, the effect went away. So I was actually going there running tests and doing stuff, and I could tell when the AC was on, you know, I could tell there were air effects. And so unfortunately, that happened right at the time of the NIAC phase 3 application and some of the replication work that was being done. And so that was kind of a setback, right? Whenever you have that kind of thing with experimental work, it's a setback. Putting it back in the vacuum, what had been happening is that the frequencies we were using, they were optimized for pushing air, right? And by itself, that's probably an accomplishment because, you know, that's not a well-known mode of impulse with the air, right? You usually don't use that to vibrate air. You don't usually vibrate air to get motion, right? There's other ways. You use a fan, other things you could do, right, to create vorticity and stuff. So anyway, so that's, you know, an aerospace group. Someday we'll probably want to look into that maybe, but we put the experiment back in the vacuum, and it took, you know, a few steps back at that point. The frequencies we were using, they were no longer working, of course. I mean, we had at one point we were able to have solid pulses of frequency where during that time you could see a clear push, right? It was actually pushing, and you could see there were tens of millions or hundreds of millions of force. And again, that was attributed to the air. So with that setback aside, once we got back in the vacuum, again, we started to see eventually going back and doing sweeps. It took a little time, but we started to see things progress there. So after that, one of the issues that we all noticed was the bearings were basically scorching the rods. And this was something that Jim, you know, it took me time to actually convince him. But once I found something that could fit, that was a composite, and, you know, he could just plop it in there without too much trouble. He tried it out, and we were all of a sudden going from like having to build a device and it might work a couple of times to, you know, then it was like, it just gave you almost garbage, to something where it was like repeatable sweeps, repeatable effects. And so slowly we started to make improvements in the experiment. And, you know, this was a thing, like I would, you know, sometimes you could say that it was frustrating because it, you know, would take time to make a change. But in reality, you know, this is one of the things where if Jim was not, you know, basically conservative about, you know, changing things or his ideas, he might have dropped this whole thing a long time ago, right? So so I see it as a just a matter of fact of, you know, this kind of thing, this kind of work. So eventually we got to the point where it was acknowledged that, okay, the torsion balance is the limiting factor here. And so anyway, working with Jim during this time, we had two parallel tracks. One was the experiment and one was the theory. And with Jim, initially, he tried to convince me that the theory was something that, okay, that's not worthwhile doing. We need to do the experiment, get it replicated. That's enough. That gets you a Nobel Prize, whatever. But, there's other people of the opinion that, hey, I need a solid theory. Why is this working, right? That's a big question. Like I'm trained to know that, and, others are trained to know that. And Jim understood that, it wasn't something that he could tackle on his own. He was going to tackle the experiment, which is fine, right? But in the meantime, as I went along, there were developments in observational cosmology and in physical experiments, like Eric Reiter's that came up earlier. Eric Reiter's work, I became aware of that just over a year ago. That really pushed me to revisit Einstein's program and completing that. So the last year the last year and a half, I would say, I've been intensely working on the theory side. And Jim knows this. I would talk to Jim about things, and we'd have arguments about symmetries, and I don't care about symmetries. Like, Jim, come on, that's like, okay, yeah, you're right. So we go back and forth, and really Jim's insistence on basically the doing things right in the physics, the way, the conservative way, where you're not just hypothesizing something just because it's convenient, having a good reason, good physical logic. I mean, that's the path that I was taught. And with physics, you have to figure it out yourself. No one's going to teach you, right? That's one of the difficulties. And that's one of the difficulties with communicating and with working with others, is that not everybody is understanding things the same way, but the physics is what it is, right? So we're all at different points in terms of our understanding. So fortunately, the breakthroughs that I had in the last several months, since about the spring. I think it was March, April, where things started to come together really solidly. And even then there were some issues, and those got resolved. And at the end of the day, which surprised me, at the end of the day, Jim was supportive of the theory work and actually pushing me hard to get the thing published. So the good thing is that Jim at the end got to see or understand a theory that was fully covariant, that gives you inertia, that kind of vindicates what he was doing with his theory. So he was really happy about that part. And I think his dedication, I mean, he is trying to support the work in the future, from what I understand. So I'm having meetings about that. So hopefully that will continue. Now, what I'm going to be doing is, the university has asked me to take Jim's stuff out. I have a few months. I got a spot at a local makerspace where I can, store the equipment and actually run it. That's one of the good things about that. So the work is going to be continuing, especially the linear experiment. And I'm also going to do the pendulum experiment, but in a vacuum, so that we can validate the effect with the devices we had. So fortunately, we were able to get 16 stack devices. We were able to get a third-party company that builds the stack. So they build them really well. They're highly QC'd, and so I'll be able to actually now I'll be able to make the improvements that I've been wanting to make with the mounting that Jim was a little hesitant to do. I can do them now, of course. I could have done them any time, but Jim was really driving the experiment. I didn't want to over push what I thought. So anyway, I spent a lot of time with Jim over the last few years, and we did take a few trips. We did spend a lot of time together. We took a trip to one of the Breakthrough Discuss conferences. You see the poster back there, where we drove up to Santa Cruz together. And on the way up, he had a flare up of his issue that he would have with coughing stuff up and with aspiration. And that was a tough trip, like medically for Jim, but he insisted on going, insisted on being there. He wanted to talk to the NASA people and whoever was there. So, I took him up there. That was very, very stressful, but that's a long drive for hours. So we got to know each other really well. And I was really glad for the time with Jim. It's something that, like I said, I wanted to work with Jim for a long time now. And he was one of the ones that were, I think, doing real physics, doing experimental work and thinking for himself, right? Figuring things out and having an understanding. So he knew a lot of people. Like I sometimes I'm surprised. Like there was quite a few people that he knew, I'm sure that I'm planning on writing an email to his larger list probably in the next month or so once I finish the paper. I think it's appropriate for whatever I do with the theory. Once I publish that paper, putting on the preprint servers, then I can talk about it. And I want to give him full credit for everything he did helping me figure things out, because without him, who knows if I would have had the confidence to even get to the point where I'm publishing it. So Hal is going to be, you said he'd help me out, but Hal's retired, right? So Hal's not diving in there, but really support, Hal's supportive of, with advice on what I should be doing. So yeah, that's Jim, and he had a significant other, and she's being taken care of. So everything with Jim, the university is probably going to, I don't know what they're going to do, but he was really a big reason why a lot of the stuff we're doing is serious. So especially the NIAC, the fact that he got NIAC funding. And that probably opened up NSF. We were interested in doing that, and so that's something I might go after if that's available still, once I get the experiment up and running again. So we did have plans, like David mentioned, of the molecular thruster. That's something that's a lot more controllable, and doing other things like that. But that being said, the theory itself, it opens up more than what Jim had there. So Jim's effect is one of many that we'll be exploring in the future. So I've got a lot of work ahead of me, and I'm taking Jim's example and I'm just pushing on through. So that's what I have to say about Jim.
Curtis, thank you. Thank you so much. Now, let me try and bring Michelle in, and let's see if we can hear her. Michelle, I know you're having camera troubles, but are you able to talk? Can we hear you?
I don't know. Can you hear me?
Yes, I can.
Oh,
sound
good.
wonderful. So, yeah, it's okay. So you are having camera troubles. My apologies for that. If it's okay, let me take Curtis and myself out, and I would say take it away, ma'am.
Well, it's going to be hard to follow up these other guys. For 50 years, I've been building things, actually longer than that, and during those years as an engineer, I've met a lot of people. Some have been absolutely wonderful, some have been great, and some have been outstanding. And the ones that I've met have been outstanding. I can count on one hand and still have fingers left. Jim sits in that hand. He was a wonderful man to encourage you, to criticize you, to agree or disagree with you. And the one thing you would always get with Jim was his opinion. right or wrong. You may disagree, you may agree, but it was the honesty that I admired from Jim. Back in 2015, I had been retired for a few years from my business and company, and I'd been working on Scheuer's EM drive to prove or disprove it. There was a group of us DIYers that had set up little labs and stuff to test to see if this effect with the M drive would work. And over the years, we all fell along the side and eventually proved out that the Scheuer drive does not work. And I was kind of floundering for a while, but I got invited in like 2016 to go to the Advanced Propulsion meeting up in Estes Park in Colorado. And so I went. And there I got to meet all these wonderful people that supercharged any work that I may be considering. And I also met Jim at the time. I remember meeting him sitting on a bench outside the lunch hall. And I laughed with him, and I turned and I says, "Is this like the Group W bench?" There's an old story with that, and a movie called Alice's Restaurant, that everybody's sitting on the Group W bench, and beholding that, he just started laughing. He knew exactly what I was talking about. So we talked a little bit about what he was doing, how he was doing it, and I said, I had a brilliant man one time, a real smart man one time, by the name of Green. Dr. Green asked me, or told me one time, that if I wanted to know a smart man, ask him what inertia was. So I asked Jim, I says, "What's inertia, Jim?" I thought I was being cute. His eyes lit up, and he proceeded to tell me what he thought inertia was. And it made a lot of sense to me. And I was enthralled about what he was doing and how he was doing it. A few years went by, and I think it was in 2020, like in July of 2020, I was asked to join the Woodward group. I said I'd be honored to. So I joined the group and started to learn about propellantless propulsion. Started learning about the Mach effect. And eventually, after about a year or so, doing some contributions from an engineering side point, I built my own lab, set up several different experiments to run, air slides, torsion arms, vertical counterbalance torsion arms, designed one from ground, and pendulums, and eventually went back to linear air bearings so they were frictionless so that we could see the effect. I also turned around and brought on board different tools that had not been found or been using too well. One was a motion enhancement software by MIT that enhanced motion of objects. So we could actually enhance the motion of the device moving around and get an idea of what was happening at a very small scale so we could amplify the effects. That also led to another piece of software called Tracker, so we could actually track all the movements of the torsion arm and the device and the springs and everything else in there so that we could take out movements that were not conducive to thrust. So so where I'm at now is that I'm building a new lab. I'm adding on to my lab, expanding it a little bit. And Jim encouraged me to do this the last time I talked to Jim when he last went into the hospital. He thought I was doing a great job and encouraged me to do that. Was to test out Paul March's MET or and also test out KS drive that I was working on, which is a hybrid of not Scheuer's work. It was all it is basically I just use a cavity and modified it extensively to incorporate Woodward's effects into it, the Machian effects, and several others. So that's where I'm at. And I'm, instead of calling it Shell Labs, I think I'll call it Woodward Labs. If you'd be okay with that. Or if I find anything to dedicate something to him, because I do miss him. And that's about all I got to say. Thank you.
Well, Michelle, thank you. Thank you. And I know it was difficult. I can hear that it was not easy, but thank you for sharing that.
Yeah, I'm kind of at a loss for words here.
Oh,
which is not everybody that knows me know that I'm usually not a loss for words.
If it's okay, let me bring Chris in. Chris, welcome, sir. And you wanted to say a few words as well.
Hey, Tim. Good seeing you again. Can you hear me?
Yeah. And yeah, we'll give Michelle and Curtis and David a few minutes to just kind of relax and say, definitely tell us about you. Tell us about Jim.
Jim's a really good man. I actually stumbled upon Jim's work fall of 2021. At that time, I was looking for propellantless propulsion solutions for my work at Cochrane Exploration. At the time, I reached out to him. He was actually very gracious, and I actually distinctly remember New Year's Eve of 2021, Jim being in his lab and me being on a Zoom call with him, watching him run experiments. I'd actually had many conversations with him, and to kind of everyone's point, Jim is extremely encouraging. I told him about my work at Cochrane and just what I'm looking to do as far as starting this aerospace company. And I appreciate all the guidance and effort. Like Curtis, I've got his book as well. I had the opportunity to spend time with Jim at his lab twice. One, just kind of getting to know him, learning the setup, and then coming out a second time. So this was in early 2022. I think the second time was late 2023, actually spending time with him, learning to build the stack. I actually remember it may have been March 22, talking with him and actually getting invited to be a part of the Woodward group. And just always looking forward to our Friday evening calls and just working through experiments and having discussions and figuring out ways to improve this. So once again, I appreciate Jim, all of his encouragement. I appreciate, being able to meet and work with the team and become good friends with them. And, I'm just looking forward to continuing Jim's work and continuing with the team and moving his vision forward. So I'll definitely say I'll miss him. And that's all I can really say at the moment.
Okay, sorry about that. Hit the wrong button. Chris, thank you. So let me bring, I think that was everybody that we had. And then I'll bring Curtis on. And yeah, so guys, thank you all. Thank you all. And you know what? For just a moment here, let me bring everybody in. That's everybody that we have in the studio. And
let's see if anyone has questions
guys
or anything.
a giant applause. This is a little more somber moment, but yeah, I mean, if you want, you know what? Let me do this. I can share really quick. I did video with Jim, but I also I took some photos, and so I wanted to share this. You guys have probably seen this several times. This is Jim's lab at CSU Fullerton. I took this photo from his house. I will drop a link into chat from that. you know, I know that the lab is changing and you guys are working on the equipment and updating everything. So these photos are already outdated, but in a good way, right? So I'm just grateful for the opportunity to come there. And you know, I'm happy that I was able to capture some photos of him doing what he loved while he was still with us. And I got lots of photos of Curtis also.
Oh
Curtis
no.
was, yeah, you were there.
And now
Curtis
he's
was,
a physics force ghost, so maybe even more powerful. I don't know.
Yeah.
yeah, and David Chester came to visit as well. And just so you know, I mean, you guys are welcome to use any of these for anything. You can, if you click on them, you can download any of them. You can download full resolution. And if you ever need the video or anything like that, the Space Studies Institute, okay, there we go. The Space Studies Institute used one of those photos for their when they did the eulogy for him online. So
Yeah. Yeah, and I did talk to his attorney, and he didn't ask for a service, so there was nothing. No one missed anything, if you guys were wondering, because I've been people emailed me and texted me, and I didn't reply, but yeah, there was nothing that he wanted to do, but yeah, I think this is good. Also, the ST Spark, you know, one of those conferences were dedicated to him. I think it was 75 at the time. You know, one that Hal put on. So that was good. But you guys have any questions about Jim or anything you want to ask?
I wanted to say, like, I came to Jim through my own pursuits, and I'm absolutely nobody, and I know nothing, relatively speaking. But Jim answered them forthrightedly and was just very cordial and humble, and also no barrier, you know, to entry with him. Like, he's not one of those gatekeeper personalities. He was just very helpful, and I'll miss him too.
yeah, you know, the thing that struck me was he was so determined. I mean, he was so diligent. He was very precise. He was incredibly rigorous scientifically, and he was so determined. You know, Curtis, when I visited, he was having, as you remember, he was having significant medical issues then, and I was struck by how incredibly determined he was. Just this amazing perseverance. You know, I mean, he would go to the lab and do his tests and stuff, and there were a couple times. I mean, the first night that I came to see him, we spent the night in the hospital, right?
Yeah.
And that was the same issue. And I know that you spent several nights with him similarly.
Yeah.
So,
yeah, it was really rough, and I think Jim. I mean, he had certainty about these ideas, and there's a good reason why, right? so you know, that I know it's a school of thought that's fallen by the wayside, sort of in mainstream, but that's okay. You know, things like that happen. There's still people still understand the questions about inertia and getting that answered and how important that is. So and that's what Jim was trying to do. So, like I said, at the end of the day, it looks like we have something, and we'll see.
yeah.
It's yet to be determined, but I think when I can talk, when I'm ready to talk freely about it, I think you'll all understand why Jim was happy about it. So that's at least that's a kind of a good thing that happened there. It wasn't something where, you know, unfortunately. So I kind of briefly talked about Roland Winston. He was another one of my mentors. He was my advisor at UC Merced. He actually passed away in the spring. So he was also one of the people that I was talking to and getting, you know, advice from as I was developing this thing. And unfortunately, it was like last year where he was no longer able to talk, so I couldn't call him anymore. But yeah, it's you know, that generation, they're getting older. I actually when I went to Roland's, I got Roland's gravitation book. and I looked inside, and it's signed by Ray Chow. So, I don't know if Ray gave this to him, but or if Ray wants it back. I don't know, but yeah, all these guys are, they're pushing physics forward, and that's what Jim was dedicated to.
Yeah, we have lost, and this is the natural progression, right? I mean, this is the cycle of life, and it affects the sciences, it affects small communities. It's not just ours. But it's difficult. And like for me, I was incredibly close with Paul Murad for 20 something years. He was like a second father, and when he passed, that was really, really difficult. But there have been several other really remarkable scientists, and in so many ways, it's such a tragedy to lose that knowledge, right? But at least we have a community that's able to carry on, what they're able to do. So, and in terms of what Jim was doing, I mean, you guys were so much closer to him than I was. I knew him like professionally, and I had done a couple of interviews with him, and I was friendly with him, but I wasn't close to him like you were. And so I'm glad that you were able to speak about what he's doing, and I'm glad that you guys are able to continue on his legacy. And Michelle was talking about like Woodward Labs. I think that would be a wonderful name for it, because he kind of outlined a vision, right, and said, okay, this is where it could go. And in science in general, that's where it always starts. So many of these things are generational projects, right?
Yeah. Yeah, and hopefully we can get some replication of these experiments that are important. I mean, I think I know Eric's experiment needs replication. Jim's experiment needs replication. And I know there's a push to say, okay, well, what's the answer at the end? Where's the propulsion? But there's work to do, right? Drew knows this. He knows there's a lot of work getting the stuff working.
Yeah. But it's moving forward. It's like progressive. It's iterative work, right? And again, that like with Jim, he laid those foundations, and I know that you guys helped him lay those foundations. So this wasn't just him, but part of what your group did was create this basis where now iteratively you can make it better and better and better over time. And that's what Drew is doing, right? With the thruster he's working on with Dr. Bueller, is they've laid this foundation and said, okay, we can create this effect, and we really have something. And you know what? Maybe we're not going to make it 100 times better tomorrow, but we can make it a little bit better. And the next day it's a little bit better. And in their case, well, and I think in your case as well, right? It's millions of times more force than it started with, if I remember correctly.
Yeah. Yep.
Yeah. So it's iterative, but that's amazing. That's the basis for it.
Yeah.
Also, it was hundreds of years from Newton to Einstein, and it might be hundreds more, but before the next major advance, because it goes with human paradigms as well, and it's social changes, and sometimes ideas can stick around for a long time before they're adopted. But direct force, or call it like propellantless propulsion, is such a game changer and such a paradigm changer. It makes sense that it takes some time to brew, and Jim's just like on that cusp. So
well, and Brendan, this is and this is larger than just Jim's legacy, but I think that we're all the beneficiaries of advances in like communications and networking technology. And that is like in my mind, I'm always trying to look at this and say, okay, what's changed that we can really leverage, right? And with the propulsion stuff, a lot of these ideas, the technology in many ways was there to do these 50, 60 years ago. But one of the big things that's changed is the networking so that we can work together. And I think AI is just another tool in the kit, right? But like my hope is that by leveraging all of these, we can shorten that path to making it all better, and that's not just APEC. That's, I mean, one of the things that I've seen over the last couple of years is more and more little working groups starting to form where people just set up Zoom calls and they get together every week or so, share results, and support each other. And that is so amazing because, like, when I first got exposed to this area, it was all like email. And 10 years before that, it was all letters, right? And when you think about, the information that you're limited with a letter, and then it takes a week or two to send it, but, so now people are able to collaborate and watch experiments in real time. That's giant.
And it's in the realm of ideas too, instead of ability, as long as we see AI as the tool instead of like the oracle, and that it can effectively, it's up to the humans still to have Gedanken experiments, to have thought experiments, because we have an inner reality. We don't know that AI has an inner reality per se. They may have some version of it, but it's completely alien to us, and might function its own way. So, like, it's still up to us to be in the driver's seat there. But yeah, definitely that all accelerates the process.
Yeah. Well, guys, we're just about at the top of the hour. Does anyone have any final words they'd like to share about Jim? And we can go into open discussion after this. And again, I should apologize if I botched things in terms of moderation today, because I'm quietly fighting one heck of a flu. Yeah, Drew, go for it.
Oh, yeah. I really didn't know Dr. Woodward, and I think this speaks more to the group around him, specifically Curtis and Chris and all the other people and David that worked with him specifically, that he is remembered for being an amazing person that touched many lives, and they're willing to change their lives to carry on a work that he felt greatly in, and now they're coming to see that it's something worth pursuing. That the ability to touch lives is don't get me wrong, his scientific achievements and his engineering achievements were probably amazing. I really don't know that much about him, but I can see that he's touched a minimum of 20 lives, and most of these people are just cold-hearted like me. I mean, I'm just an engineer. For someone to be able to come into my life and touch me and have me follow them, that just speaks beyond words to the man's integrity and his humanity. And I'm just gonna leave it at that. Wish I got to know him better.
Yeah, no, and again, I didn't know him nearly as well as the folks on his team did, but my every impression, every interaction with him I had, he was an absolutely remarkable, absolutely brilliant person. And he avoided a lot of conflicts too. As you know, in our community, right, there are a lot of scientific conflicts. He avoided getting sucked into those. He avoided getting sucked into the fights. He kind of kept his head down and his nose to the grindstone, and he kept doing his work, and he was doing rigorous, diligent research. So, well, guys, why don't we open things up? It's 4:00. Why don't we open things up for open mic? Michelle, if I can take you out if you're having trouble. That's
okay.
Okay. Well, thank you so much. Thank you so much for your thoughts.
Yeah. Drew, you said it very, very well. To have somebody come into your life that changes your course and enriches your life, to do something that may make a change in humanity is an incredibly wonderful gift. And Jim had that gift in spades. Not only did he have the brilliance of being able to see how things work beyond the norm, he was able to inspire it in everybody else. And over the years, we got to see a lot of people come on board with this group, and they're not here now, but Jim also changed their lives. So wherever he's at, I hope he's looking down. I hope he has a lot of the answers. And thank you for the invite.
Oh, absolutely. Well, Michelle, thank you so much. Thank you so much for your kind words and your thoughts and your memories.
Yeah, I feel like I'm sitting on the group W bench again here.
Okay. Well,
nobody knows. Only the old people know what that means.
I'm a young people, but I'm Googling it.
Okay. Well, thank you again, Michelle. Let me take you out. Okay. And then, because I can tell she's struggling a little bit, and yeah, she was really close to Jim. They worked a lot together. And Curtis, I'll hope you're doing okay too, because I know that it's not easy. It is not easy.
No, it's not.
Yeah.
So the university is giving me a couple months to move things out. So I'm going to be. I did, like I said, I got a spot at the makerspace, and so I need to start getting that process done. I was hoping to be at his lab while we did this call, so I can show you guys around. But unfortunately, the hallway that's usually open to get to the lab, it was closed, and I don't have the key to that one. So I can get in the building and get in the lab, but the hallway's closed, and it's a Saturday, so there was no one to open the door around. So yeah, I couldn't go in there. But I do have pictures of the lab. I went and took pictures last week. And like I said, I'm planning on getting all that stuff out. And at the same time, I need to do some provisional patents and write a paper and get all this stuff done correctly. So it's quite a bit of work. Probably more work than the unification itself. But anyway, I'm actually right now working through using Mathematica to check all my calculations. I'm going methodically through it with that, just to make sure that I didn't do anything boneheaded before I put the paper out. But conceptually, everything is good in terms of. I mean, this legacy Jim is leaving, having worked with me on this. This is going to be substantial, I think. And even if it just turns out to be only an extension of GR, that's enough. So, yeah.
Yeah, there was so much there. Well, and again, we are an open discussion, guys. So, you know, whatever comes to mind, I guess, that's appropriate for APEC. Yeah, I mean, I can tell you one of the things that I just got into this a couple of weeks ago. People have been teasing me about not using AI for the last few months because everybody else uses it. And so I've been the old stick in the mud. And so I'm finally starting to use it to write summaries. And then I'm extracting summaries I'm using that tool to extract summaries from videos. And then I'm using ChatGPT to rewrite those and add relevant information. And so one of the hopes that I have is being able to I mean, you guys generate so much material, not just the mathematics, which I don't know how to get yet, but like ideas and thoughts and history. And so now I'm at least finally able to capture some of that and put it online in a searchable format. So that's kind of what I've been doing lately. So I'm hoping to, with the Alt Propulsion website, like I have 2 or 3 videos from Jim up there. I have one with Curtis. I mean, I think I've added probably 80, 85 in the last couple of weeks. What I'm hoping to do is get that information out there so that people can understand better what's going on. Sorry.
Jared, did you have?
Yeah, I wanted to take it back to an engineering thing. Something that I saw this last week, Curtis, that was reminding me of your stuff, Woodward stuff. Magnetorheological fluid. So this stuff is like ferrofluid mixed with non-Newtonian fluid, right?
I know magnetorheological fluids very well. And actually, initially one of the grad schools I tried to go to was Cal State Long Beach, and they worked on that stuff there. And I was going to do theory I was going to work with the theoretician that was working on that. And you find out when you're a physics grad student that all you're there for is to do the math for them. So I was like, no, I'm not interested in being Mathematica for you. But yeah, I'm very familiar with magnetorheological fluids. And so in terms of the Woodward effect, one of the things we looked at is besides piezoelectric, there's magnetorestrictive materials like terphenol D that you can have a lot of energy. But go ahead.
Well, yeah. So what I was seeing with it, just so everyone's on the same page, so this non-Newtonian ferrofluid, MR fluid, the idea is that it can change its viscosity depending on how much of magnetic field you put it in. So for like shock absorbers for high-end cars, that's the one place I've been able to find where people actually use this stuff.
Yeah.
But the part that got me thinking about the Mega Drive was this lets you move the effective mass in very unique ways, right? And so instead of having solid masses that are vibrating, asymmetric vibrations, right, to get it going, this lets you have a liquid that you're using magnetic fields to be able to move around and convert it from a very chaotic to a more ordered state, right, back and forth. So I was thinking there might be a loophole somewhere in there where you can use this this non-Newtonian aspect of this fluid for some of these interesting inertial effects that you guys are doing.
Yeah. Yeah, I get what you're saying. So one of the things with this that's tricky and what you're bringing up is something that, maybe down the road, but one of the things that's tricky is actually getting the tuning between the mechanical and electrical system. And David is well aware of this. So what we hypothesized was that basically if we prove the effect, the next step is to do something in the MEM scale. Because when you're doing those kind of scales, you can engineer things like you want. You can use microfluidics. You can do a lot of things that you can't with bulk matter. It's just going to be what it is, right? You don't have a lot of control. Whereas when you're, doing semiconductor processes, you can actually tune things the way you want them. So, and that points to the whole metamaterials discussion, where that could be something.
Maybe if you have like nano powder, right? So you could cheat for your MEMS device, and rather than have to engineer something at the very small scale, you can buy off the shelf nano powder and make your own MR fluid that way. And then you could have responses and sizes of these things going through very small channels.
Yeah. So MR fluid, I mean, what it does is it changes viscosity, right? So what that would affect would be the way the impulse waves travel through the bulk media, right? So that what that would do is that would allow you to maybe open the range where the tuning would be with the electrical and the mechanical side. That being said, the experiment that we were running was basically an oscilloscope with whatever we had, whatever we could punch in buttons. So we were doing a sweep, it was a sine wave until, Paul and David and I talked about, okay, let's do do a triangle, and then like, oh, let's do it like 95%. So it has higher dPdt, but that's as sophisticated as it got in terms of like so far. But I think one of the low-hanging fruits is to actually use a more complex electromagnetic wave to induce the effect, right? Because then the bulk material effect can be taken into account, and you can, the thing we have control over, the thing our civilization is really good at is electronics and electrical stuff. So there's a lot there. There's a lot of room to grow there. I mean, we were looking at like, generators where arbitrary waveform generators where we could control it a lot more elegantly and have some feedback and that kind of stuff. So we never got to the point where that was something we did. So there's, what you're talking about, that's probably something for optimization down the road. The other thing for optimization would be like the mounting, right? So once the effect is proven, I mean, it's really a no-brainer. You're going to want to magnetically capture it, because anytime you're touching something, that can dampen the effect. So the reason we don't do that is when you put magnetic, the reason we don't do that is this is still a physics experiment. So you need to prove the effect. And if you have any magnetism around, people are going to point to that and say, oh, that's what it is. So we got to get past the stage where it's an physics experiment, it's proven effect. Once it's a proven effect, then we can go back and engineer a magnetic capture. And so that way the thing is free to vibrate and we can like put energy in and do what we need to do. That's kind of, I mean, that's an obvious thing. I'm saying it here, it's public, but it's obvious. Anyone can think of, think of that. But yeah, there's optimizations that will come down the road. Definitely, Jared.
What happened to Timmy?
What's that, Drew?
What happened to Tim?
He probably had to step out.
Yeah.
We don't have any other questions for David or Curtis. Yeah, Drew, maybe we can see what you've been up to.
I just wanted, since we're talking about new cool stuff we saw this week or last week or whatever, this is something out of, the Coyote and Roadrunner, because this is so far out of anything I've ever heard of that I don't even know what to do with it. But this is straight from DuPont, the people that actually understand this stuff. This is a sub-percolation carbon black infused polyimide. And what I'm told is that this has the same electrical properties, for the most part, as Kapton HN, which means it can hold back an enormous amount of electrostatic force. But it also is just underneath the conductivity. So even though it's black, cameras, even though it's completely black and it's totally opaque, this is 5 mils. This stuff will not conduct electricity like an ESD version. They make an ESD version of Kapton, which it's got a couple of million ohms per inch, just so it can bleed off charge. This is not that. This is what they call below the percolation zone or number or ratio or whatever that word means, so that there is carbon in here, but it's completely contained within the polyimide matrix so that it doesn't interconnect. The resistance on this is like 10 to the 10th something. There's some number after that, and I'm going to guess it's ohms, but it's some area thing. I don't know. We got a new Sparky on our team, and he understands it, and I don't. I don't really care because he understands enough of it. But the dream is to use something cool like this to be able to achieve what I'm about to show off in my lab notes faster. Because right now it takes about 20 to 40,000 seconds to get to maximum thrust in one of my thrusters. They do get there, but it takes anywhere from 20 to 40,000 seconds to achieve maximum thrust. And that's a long time. That's a very long time. That's like 5 hours, 5.5, 8, 10 hours. So anything that can get me there faster is worthy of investigation, and that's what I want to show off is Kapton. Actually, it's Kapton MTB. Good luck finding it. We had to go to China, even though it's made by DuPont. They don't make it in the United States, and it's going out of production because no one uses it. So, see a cool thing I found this week.
That's really cool, Drew. So it sounds like that stuff is like Kapton, but it's going to let you.
I can barely hear you, Jared.
Oh. How about now? Can you hear me now? It might be on your
I guess, yeah. I mean, I just turned my speakers up. All right, go ahead, Troy.
I was going to say, it sounds like you found a replacement for your Kapton, but it's better because it lets you charge up orders of magnitude faster.
We're going to find out. The Sparky tells me that with some electricity, with some really tricky things and some diodes and some things I've never even heard of, that he's going to be able to cut my charge time from 50,000 seconds to 50 seconds. And he's going to be able to increase my spatial charge, which is the real electrons being jammed into the plastic, by several orders of magnitude. And since thrust, in my case, is equivalent to, or at least proportional to, bound charge, every bound charge that gets in there makes more field, which makes more thrust. So I'm very much looking forward to next week. I basically took next week off just to play, because that's my staycation.
Nice. Also, a big congratulations is probably in order, because yours and Dr. Bueller's stuff was just featured in Popular Mechanics a couple days ago.
Yes, it was. Dr.
Congratulations.
Bueller, thank you. I'll pass it on to him. He only takes invitation now. To even speak to him now requires an invitation. You got to go through his secretary. He's become very important to himself. But no, we're excited. His I don't know, view count is over 60 million now across the spectrum. It's insane. He gets groupies. He's got groupies now. He gets calls daily. He gets emails, hundreds of them. Everybody has a theory. Everybody has a dream. I can't tell you the number of people that want to join my team that I've never heard of, which is cool.
Did they re-release that article? I'm looking at it in.
I think they used the second one, Tim. I think they based it on the most recent one you put out.
Because they had one in June also, and I thought it was the same one. That was why I was looking at it. I was like,
is there a link available to the paper yet? That's out there that I can grab and share?
I just shared in the private chat the link to the Popular Mechanics.
Okay, is that got a link to the paper? Or?
No.
Okay.
No. And I don't want to sound mean, but we've got to get past our fight with the patent office before we release the paper, because the paper immediately shows you how to build the next generation of thruster. And until we get past the patent fight, which, by the way, the U.S. Patent Office sucks, okay? They are not in it for the people trying to move civilization forward. They are, I don't know what they're in it for, but I'm the first guy that's had to produce a working patent in their office in 100 years. I have to take a working version of my machine to Washington, D.C. and show it to them before they'll issue my patent again, which is based on my first patent, which they issued. So, I'm very
yeah.
Very
Drew, the thing, if I could, I wouldn't even say mention. Just remind you of one thing. It is that you guys are inspiring thousands, tens of thousands of people. I mean, every time, like you and Charlie are making headlines, right? I mean, this entire community is inspiring people. But like right now, every time I'd wondered, I got a ton of signups for the APEC list. And I was like, where are these folks coming from? Okay, it's from the Popular Mechanics article. And they say that for every one person that signs up for a list, that's just our email update, right? That's just for every one person that signs up, at least 100 were interested in it. And thousands more have probably seen it. So you guys are inspiring thousands of people,
That's wonderful. I hope we inspire lots of people. I hope people get into this field, because NASA's never going to get there. As far as I can tell, industry doesn't care. They're very happy with what they have. There's nobody. By the way, guys, I talk to really big space companies on a regular basis, and there ain't one of them out there, not one, that's looking for anything that this group is going to produce. Mm-hmm. If you created an anti-gravity drive tomorrow that could lift its own weight and the 600 pounds of batteries that you stuffed on the thing and flew it around your house, nobody in industry cares. They are completely satisfied, 100% happy with what they have right this second, which is variations on the rocket that Goddard created 125 years ago.
And that is ripe for disruption.
But I won't say who they are.
What now?
One of the big stories out there is and this was that SpaceX Earth to Earth, but I think Elon Musk was saying he could get it up to 200 tons, which was the Air Force requirement. And if so, and I'm not poo-pooing this. I think it's an achievement in its own right, but he was saying basically you could drop the cost of rocket travel down below first-class international airline tickets. Now that's really cool in its own way, but it's not the next step, and it still struggles with all the limitations that rockets have. So,
okay, I always tend to go back to my favorite U.S. history story. Okay, the United States government created the best iron lung ever created right before they told Dr. Salk, no, we're not going to fund your research for a cure for the disease. But they put millions into the development of industrial iron lungs because they said, no, this is the answer. No other problem. We don't care if you come up with a solution that eliminates the disease. We are going to come up with the best iron lung ever. Mm-hmm. That's the way the government operates.
Yeah, and I hate to say this, but I mean, for decades, I felt like NASA, and especially since the advent of SpaceX, and now with what Blue Origin is doing and the other companies, like I tend to feel like NASA should just get out of the launch game, get out of the rocket game, and focus on space science.
I feel that way too. I believe NASA should go back to what they do best, which is cut checks and slow down progress. That's what they do best.
Yeah. Well, and to be nice to them, though,
stupid decision.
To be nice to NASA, some of the stuff that they've done, we have probes on pretty much every planet. They do amazing with probes. They do amazing with the Martian rovers. That's been a breakthrough success. So there's a lot of stuff that NASA does incredibly well with. So it's just kind of like, you know what? Hey, leave the rockets to people who can do it better, cheaper, faster.
Yeah. So by the way, this year we were going to apply for. By the way, this year we were going to apply for the NIAC Phase 3, but it got canceled. So I don't know what they're gonna do next.
Yeah, we applied for about a half a dozen things. Against my better judgment, Charlie applied for them all, and they all crashed.
Yeah, that's why I was going to go to NSF instead. They've actually funded a couple of propellant-less propulsion projects the last few years. So we'll see.
The number of explosions on the launch pad for SpaceX is pretty alarming, and it feels like we're running up against a physical limit to where rocketry can get us. Where to advance further, we're going to need some sort of holistic solution, whether that's this or that, I don't know, but
it's short-term thinking, and you see that. I mean, like what Drew was saying about the iron lung, you could make the same. Like one of the areas that I'm really passionate about is eVTOLs, and that's just propellers, right? But the concept of it lets you bypass the hub and spoke road network, But again, the way that the prevailing wisdom flows, it's like, oh, we can build better roads, we can add more lanes, we can do this, we can do that. Yeah, it costs billions to do it, but and it's like there are solutions out there to a lot of these things, but that paradigm shift is really difficult,
And as far as I understand, it takes anywhere from 20 to 40 years for a technology to be accepted into a culture. Electricity, you would think, okay, that's pretty obvious. The combustion engine, the gasoline, the airplane, the radio, the cell phone, the computer. These are all 20 to 40 year cultural acceptances. Yeah. If you crack the code tomorrow, your kids are going to be the ones using this stuff.
we need to find the low-hanging fruit here too. I think, like Tim mentioned, eVTOLs. eVTOLs aren't going to really make sense for all the same reasons that auto makes sense, but for low-level applications like just simple transits across town for CEO executives or something, this is where we get our foot in the door, you know. And with what you're doing, the satellite drives to replace the xenon plasma drives thrusters that run out of juice, and then they have to crash back in the earth, which may or may not be affecting the ozone layer. I don't want to start a fight, but that, you know, that's where we can make inroads, I think. And what you're talking about with,
Well,
it's a matter of just increasing the dielectric qualities
in terms of
materials.
Brian, in terms of lock-in, like a couple of other amazing tragic examples are battery technology, right? I mean, like I'm on LinkedIn and they're having a perpetual battle about the benefits versus drawbacks of lithium and lithium mining and pollution and all that associated with batteries. There are several better battery alternatives out there. And when you look at companies like Tesla, Tesla's focused, not just Tesla, but all the major manufacturers are focused on quicker charge times for existing lithium ion instead of going to something better than lithium ion. So batteries are one example. Another is the permanent magnets, right? Everybody's using the neodymium magnets. Those are good, but there are a couple of better ones that have come out, and nobody's looking seriously at those yet. So yeah, it's like industry gets locked in. But that being said, like this happens. I don't remember what book I read it in, but it was talking about corporations and the establishment and business structures, and like they almost always get left behind when somebody new comes in, right? Like Tesla. I mean, people had 10 to 15 years to see that electric vehicles were going to be a big thing, and none of the automakers really got into it, right? It was like, oh, let's build a Prius and people will be happy with that, or let's build a hybrid, you know. And meanwhile, like Tesla's like winning races, right? Jay Leno was like, he raced his grandma and his, you remember he had his Shelby Cobra. That was the big video a few years ago. And like it was obvious that it was coming, and the automakers were just like, yeah, we'll deal with it later, you know. So
on the note of batteries, who's the guy you had that was talking about making hemp batteries from carbon nanotubes? Who was that?
Michael McDonough, I think.
Michael McDonough.
Yeah, and then there was another fellow who came up with an idea for a lithium air battery, and those have their own issues, right? Because you have to ventilate them so it can do the reaction, but that has 3 times the range of a lithium ion. And it has, if I remember right, the scientist who's doing it said it has no fire potential.
Biographene, Michael McDonough. And then what was the other one that you mentioned, Tim? I was Googling.
So if you look and Michael Perrone has 4 or 5 kinds of batteries he's kind of excited about. I don't remember what his formulas were. I think the best theoretical that I've heard of is lithium ion or lithium air battery. And that has 3 times the power of lithium ion.
So here's the thing, right? With any of these things, any of these advances, I mean, Drew's right. It takes forever, right? But there are some things where if you show there's a clear, rational, proven thing, people will pour resources and do the advance. An example is the semiconductor, right? So back in the day, Moore was like, okay, if we shrink the transistor size, we not only get more efficient, but we get like more calculation, right? It's a lot better. And actually, it was a guy at Caltech, Carver Mead, who actually proved that, right? With using physics and engineering, and actually did the proof. And because he proved that, all of a sudden, people were convinced. They started throwing money in and backing it, right? So that's the kind of thing that needs to happen with any of these things, where it's like, oh, there's an obvious advantage, and yeah, it's hard to do it, right? It's hard to shrink transistor sizes, right? You got, it's a big effort, right? It's not one person. It's like companies and organizations. But it's worthwhile doing, right? So things go toward it. So I think what might happen here is if we start showing that there's effects and start proving it rationally, where there's like not talking about, okay, some UFO, and you can't show it, it's not a thing you can show over and over. It's not a repeatable thing, right? It needs to be a in the lab, like Drew's thing and the thing we're doing here at Cal State Fullerton, where you can replicate it, right? Someone can build it, they can see it work. It does what it does, right? So that's the best you can do, right? Because if you convince people that, hey, there's a theory, and by the way, this whole unification is liable to, basically get us to that point where we have a theory and we can show all these effects are consequences of it, and it's no longer, there's no more confusion. It's going to be clear what's there. So there's potential to have that type of effect happen with this if we keep on plugging away at stuff. But that's how those revolutions happen, and they have, it takes time, right? It took time to get to the, to the semiconductor, to the devices we have now, the nanometer devices, from wherever they were like microns or whatever, and that was stretching it at the time, But it's something that I think once we get the theory and once we can show exactly what's happening and have a bunch of experiments, like Eric, by the way, Eric's experiment I think is like an important one, because it shows the limit of quantum, the quantum thinking. And the problem is that even if you get like, these Nobel laureates saying quantum bad, quantum is not fundamental, whatever, lots of people say things, but until you get experiments to show things, the physics community is they're not gonna just listen, right? They're not gonna listen to wisdom. They listen to, experiments need to show them the way. So us understanding matter and what it really is, and that Eric's experiment gets to the heart of that, right? I hope somebody I don't have time, otherwise I would replicate it. That's a great paper. Whoever replicates that is, that's going to be big. So, and there are other experiments out there that show that what quantum predicts is not what they see. There was a guy that he had some Mach Zehnder interferometers, and they built an experiment with multiple of them, where the light would go to one direction, but at another place you could see that there was energy still there that would eventually cancel out, right? But you could see that it's not a quantum effect. It's a continuum effect. I'll put it that way. So that's with light. Now, what Eric's doing at higher energy, when I saw that, I realized right away he nailed it. Basically, he used to call it the unquantum effect, but he stopped doing that because people would get insulted, so somehow, for some reason. But all these things I think are going to come together and point the way towards and potentially bring in a bunch of funding. Now, that's another thing. In terms of going forward, like I was looking at the example, you guys know about Eric Lerner. He's the Big Bang Never Happened guy. So he does plasma research. Over the last 8 years, he's been doing that, and he's been funding his research through crowdfunding, and it seems quite successfully. So I think that's something that I'm going to probably look into modeling. I think it's a good way to go, especially you don't lose control to venture capitalists, which are, I've been in startups before, so I know what it's like. So that's something I'm trying. I'm trying to figure out ways to continue. But yeah, I apologize for not having the papers done and being able to tell you guys what is what yet. But hopefully, it won't take hundreds of years, Brendan. And in a few months here, we'll be able to talk about it. So, yeah. By the way, have you guys seen Carver Mead's talks? His Kyoto Prize. I know David has, but
I've had it bookmarked for weeks to take a look, and I mean to.
Yeah, you should take a look at his work. And what's interesting about it, he points out all these experiments and says, "Hey, we got to figure out what's going on here." So there's like a lot of subtleties that he puts out.
Incidentally, I didn't want to cast aspersions on anybody's efforts. By the way, I meant to refer to like the complete paradigm shift, which is the general use of these things in the public sector, and that we're at the top of the S curve of adoption, and it's everywhere. Like airplanes were obscure and few people trying a few different things, and all of a sudden, boom, there they were because of this exponential adoption curve. We're just not there yet, but like the interest is definitely there, and we're at those nascent bits, and so it might hit a hyper curve here in a second, and that would be a great surprise to have.
Yeah. No, I think it's going to take time. It's going to be more like the semiconductor industry, right? You got to have it may be a little faster because of technology now, but in our computational abilities. So we should be able to like do these things quicker. But adoption, it's going to take time because there's engineering effort and real resources that need to go into it. And single efforts like Drew's efforts and our efforts are going to only carry you so far. Right?
Hearts and minds have to change, and we're in a world where Brian Keating is writing hit pieces on the whole community. It's like that's the world we live in.
Bro, Brian Keating is writing what?
Oh no, he's just down on the anti-gravity people. Sort of lumps us all together. And not to
Isn't
say
he a string theorist.
He's an experimentalist, which makes me think like he should be really.
He's that guy down in San Diego.
I think he's at UC San Diego. Yeah, he's got a pretty popular podcast, and people like Thunderfoot and others that are big on YouTube that are debunking this or that. But if you can make it past the ghouls, you've got somewhere.
Hey, but we got Joe Rogan on our side.
So about Brian's
Keating, great. He's just
what's going to be interesting, Brendan, is that as a side thing, this happened last week. So I took the theory and I said, okay, what if I do the Schwarzschild solution, right? In GR, you have the Schwarzschild solution. I did the Schwarzschild solution, and then I got this result, and I'm like, wait a minute, that looks like dark energy. And then I did the same steps for the whole field, and I ended up getting dark energy. So the same effect that causes inertia causes the dark energy that we observe. Anyway, I should just shut up. So look,
as they say in Doctor Who, spoilers.
But we'll talk about it. I got to verify things in Mathematica, and that's what it is. So I got to get things checked. But once everybody understands this, it's going to be like it's one of those things where like, oh, duh, you look back and you're like, yeah, that's obvious. We should have known that. That's what it's going to be like, Brendan.
An interesting cross point with patenting, what Drew was saying, which is I happen to have just gone through business school. That's my particular pedigree. And in law, we were talking about patent law. And one of the qualifiers for a patent is that it's not obvious. It's not based on some universal principle. You can't patent things that once you discover them, it's like, wow, that's like a principle of the universe that we now know, and you can't patent that, right? So at that point, it's just various garage bands that are, so to speak, like tinkerers that are messing with the same fundamental principles and trying to find better materials and beat each other in the arms race to like rocketry itself. Nobody can patent the rocket.
Yes. So an example, so electricity, right? So if you're early in the days of electricity, you can't patent electricity, but you could patent the electric motor, You could patent the light bulb, right? You could patent circuits. So that's kind of where I'm at. I'm like looking at it and say, okay, what are the obvious applications? I'm going to put some provisional patents, and then I'll go argue with patent attorneys after about the final one. That gives me some.
How much do we owe Tesla because he was cool with Marconi playing with his ideas to make radio happen?
Yeah. So there. Yeah. That whole thing is that's a nightmare on its own. So I'm going to be getting help with that for sure, because I have enough to do with unifying physics, and then and then the experiment. So the experiment's important because these experiments, they show that there's something there. Reiter's experiment, there's a lot of others out there. There's anomalies, right? There's unexplained things. You guys know quantum field theory is like the mainstream theory, the main theory that we learn. In quantum field theory, its prediction for the dark energy is 120 orders of magnitude too high. So that's like the dark energy problem. There's a fundamental problem in theoretical physics that, there's no solution for with the conventional physics, but it's ignored, right? Because on the one hand, it's like a quantum theory. It's like on the one hand, it's the worst prediction. On the other hand, it gives you the electron to all the orders, right? But if you look at what they did, if you understand the math, it's like they're like fitting it. It's like back fit. And you've seen that math, Drew, that Dr. Charles is doing, the quantum electrodynamics. That stuff is just like, I mean, it's easy to fool yourself in physics. I'll just say that.
Yeah. I was going to say, you better hurry up with that, whatever it is you're doing, because I'm hearing words like there is no such thing as gravity come out of Charlie. So whatever the hell he's working on, he says he's got the whole dark matter, dark energy, gravity, whatever.
But Drew, there is no such thing as gravity. Gravity doesn't exist.
I really don't care. I really,
it's an
really
emergent infodynamic property.
I really don't care. I've built a piece of plastic that can defy whatever the word is that you want to apply. So, but anyhow, can I go ahead and do my thing because the wife wants to watch a movie, and I'm just going to give a quick update and.
Yeah, go for it, man. Do your screen share.
It was nothing but sadness until about noon today. Okay, so I'm going to try and figure out the present button. Share screen.
Yeah, I know they changed it, didn't they? This is one of those days. Like everything has changed. It's just like
entire screen 2. This is written by people who did Creo. Share. Did it happen? I can't tell. I have no idea. Did anything happen?
Let me see.
No,
not there yet. Yeah, there it is. Add to stage. There we go.
Okay, we're on time delay. All right, awesome. Okay, so I want to preface this with I hate electricity. I hate everything about it. I don't understand it. I don't know the difference between a capacitor and a diode or a resistor or a battery. I just hate it all. So I decided, stupidly, to check to see if my digitally controlled high voltage switches were doing what they're supposed to do. So I took out my voltmeter and I turned on the system and I brought up 100 volts on the unit and it said 10 volts on the meter and I freaked out. And I ripped every piece of electronics apart that 4 years of building put together, and that's what my shop looked like at the end of my investigation, only to find out that voltmeters operate on 10 mega ohms, and I have a 100 mega ohm resistor in my system, and that generated something called a 1 to 10 voltage divider. Nobody explained any of this to me, so I discovered that I didn't know how to read a digital voltmeter. All that said, it's real easy to do something wrong and rip your system apart looking for a problem that doesn't exist. Fortunately, it only took me 6 hours to put it all back together, and then, so this is the actual test stand right here. This is where that's the magic right there. in its ripped apart state. And that's the power supply that goes inside of it. And there's the force meters. And I have a second force meter now sitting right here that gives me the drift rate of the thermal gradient in the chamber, because these stupid meters are sensitive to temperature. So I can now determine the difference between making thrust and just the drift rate of the system. So a lot of good came out of the last couple of weeks of redesign and rebuild, but it wasn't worth this. This was a nightmare. Just to let you know, while y'all are calculating all these wonderful parameters about the universe, this is the real side of those tests. It's 100 hours of this nonsense to every hour of something actually being tested. So I'm going to shut that down, and I'm going to open up and start, I think, here. August 23rd. Is that what? Yeah. Okay, this is like last week or 2 weeks ago. I'm losing track. Anyhow, as I was talking about the drift curve, it gets hot in my shop. The hangar gets hot. The vacuum system is just out in the hangar. It's 100 degrees, and when I turn the system on, before I bring any power up on the thing, I can watch the meter drifting upwards. There's no thrust being made here for the first 500 seconds. It's just drift. So I just go ahead and draw in the drift line, because the drift line doesn't change. It's this way it's 12 hours of drift up, and then it levels off for an hour, and then it's 12 hours of drift down at night. I have done this dozens of times, so I know this is what it does. But anyhow, turn on the power, generate thrust at around 15 to 1800 seconds. It kind of maxes out on all the thrust that it's going to make for this particular set, and then it just basically follows the drift curve continuously. So I turned it off here. The red going up is the system going off. So just to give you, this is just a point of information. This is a couple of weeks ago, and this is a 4-plate thruster set. So this is 4 plates making thrust. All of them combined made about 1,750 micronewtons. Not bad, really not bad. It's about 300-ish a unit. Actually, one of them was dead, so it's only 3 plates making thrust. But I didn't find out about the dead plate until I took it all apart. So this is where I was a couple of weeks ago, and let's see. See if I can get this right today. Yeah, here's test number 1 today. Now, some materials have been changed, some shapes have been changed, some manufacturing technologies have been changed, all of which, fortunately, iteratively worked. And I'm just going to read you the notes in case you can't see what they say. But actually, I need to be able to read them. Let's see. Okay. In this particular, this is 1 plate, and it made 6,300 micronewtons of thrust. No, I'm sorry. It made 6,000 micronewtons of thrust. It kind of maxed out around 3,500 seconds into its operations. So it's taken a little longer than a couple of weeks ago, where it was maxing out at around 1,800 seconds into power. Now it takes about 3,500 seconds, but it is maxing out at a much greater amount of thrust. And once it maxes out, it pretty much would stay level. So the slope would continue level, and it would make that, whatever it is, it would make that 6,000 micronewtons of thrust forever, as long as you keep the power on. And again, these thrusters are drawing microwatts of power. So any one of these thrusters is in the microwatt range of actual power that it's drawing to maintain the electrostatic charge on the individual thruster. So, and as soon as I cut the power, it began to drift up at the estimated drift rate. So what this told me is that I could have kept the test going forever, but you can't run eternal tests. This is the second force meter that's telling me that when this slope is going up, the drift line's going up. When this slope is level or down, then this is the drift of the system. I've worked this out over the last couple of months. So this is the slope curve of the newest, latest design. I was very happy with this because this thing only weighs about a gram. And at a gram, that means I only need about 10 millinewtons of thrust for this thing to free float. Now, again, it's not going to lift the frame, it's not going to lift the housing, it's not going to lift the power supply. I'm talking about the actual thruster, the little piece of multi-material with all kinds of magic on it. That only weighs a gram. And I made 6.5 millinewtons. If you do the math, that means I made 65% of Earth gravity. So this plate lifted 65% of its own mass. And had it been pointed upwards, it would have lifted it up, or at least hovered. In this case, it's horizontal pendulum, so it's not going anywhere. So that was test number 1, and I was really excited about that. And then just to see if it was a fluke, I ran the second plate in the series. And the second plate in the series clocked out at 4,200. So it maxed out around 4,200, which is the difference between the furthest point on the thrust curve and where the thermal drift line would have been had, I didn't turn on the thrusters. So that's a good thing to know. And then as soon as I hit that point, this particular thruster decided that's it, that's all the thrust I'm making. It hit it at around 1,200 seconds, so at about 1,200 seconds into its powered run, it said, that's it, I'm done. I'm not making no more than 4,200 micronewtons of thrust. I don't care how long you leave me on. That's what I'm going to do. So the first test was like 6,000-ish. This one is 4,200-ish. So that's, 2 thrusters somewhere in the same zone. And then the last one, there was something weird going on with test 3. We still haven't figured that out. So this one had a much shallower thrust lift. So that's and I haven't finished annotating this one yet, but this one here, this is what the drift curve would look like had I not turned the thruster on. But as soon as I did turn the thruster on, obviously it went down. And at around 1,500 seconds of power on, it decided that I'm all done making thrust, and I'm all done at 4,650. So had I left the power on pretty much forever, it would have made 4,650, 5,000, probably would have made about 5,000 micronewtons of thrust. And when you buy propulsion on your little spaceship or on your little satellite, you're buying Newton seconds. So, there's not a lot of stuff here. This is, this is only 4.6 millinewtons, but it's every second. So 1,000 seconds into this run, I would have produced 4 Newton seconds of thrust. That's about all you're ever going to get out of one of these little toy $50,000 ion thrusters. They only got about 10 Newton seconds of total thrust on board. And then that's it. They're all done. So there's a lot of potential here if you never have to turn off your engine and you can stack these plates up, because these plates are stackable. So this all goes to say that in a couple of weeks, I went from about 300, 350 micronewtons of thrust per plate up to around 4,600, 5,600, 6,600. So that's about a 10x increase in the last 3 weeks. That's where we are. Any questions?
Yeah. So, Drew,
Drew, are
Are you able to, for the same thruster, you're getting repeated around the same amount when you repeat the?
Yeah. I'll know tomorrow. But previously, the thrusters were very consistent. They were consistently making whatever they made it again the next day and the next day. I usually keep them in for about 3 days, because that's about how long it takes to make the next set. So when I start seeing success, I'll leave them in, and then the next day they work a little better, because they've had more time in high vacuum, and as in everywhere else on this planet, you get atomic water on every surface. Well, atomic water tends to polarize. So the longer these things stay in high vacuum, the more atomic water ends up gone. So they get drier, drier, and drier, and their electrostatic properties improve. So they always make a little bit more thrust the longer you leave them in. And I've left them in for up to a week or two, and they've probably doubled in their capacity. Different designs, different earlier models. But like, I'm hoping that tomorrow this will reproduce, somewhere in the zone of 4,600 micronewtons of thrust, given that I leave it turned on for whatever this was, 1,500 seconds. Yeah. So I have seen it reproduce already.
Drew, for the record, I was wondering how you guys are controlling ablation or sputtering, if that's an issue at all, or if that's something that you've looked into.
It's a horrible issue. Horrible. We're controlling it by a manufacturing process, and contact me offline and we'll talk about it. I think it's brilliant, but I'm the guy who invented it. So
that's a really big deal, because it's a common criticism of what all this stuff means.
Yes, it is. Except, here's the deal. I don't have any way to show that. Our entire thruster, the whole thing, is inside of an ITO-coated PET box. So basically, we have a box. It's about yay big by yay big by yay big, and our entire propulsion system, including the high voltage now, everything is inside of this plastic box. Now, the plastic box is not hermetically sealed, but it is a plastic box, and it's transparent and it's metallized, so it's a Faraday shield. So even if we were sputtering metal, which we have done before, because high voltage plus metal equals sputtered metal, where's it going to go? It's just going to sputter onto one of the surfaces of the box. And I have done that. I have coated the inside of the far walls with vaporized metal. That, it was a bad design. But even if you do all of that, even if you transferred all the material that was inside the thruster to the back wall, it wouldn't matter, because we measure the force on the box. We take the whole box as an entity, and we put the force meter on the box, so it doesn't matter what you do inside the box.
That's also a really great answer to people that say your vacuum is not hard enough, because it doesn't matter. It's in a hermetically sealed box. That's crazy good. Awesome.
And anybody that thinks that 6 times 10 to the minus 6 torr isn't a hard enough vacuum to do this, to experiment with this stuff, does not understand vacuum. So,
you're always going to say these things. It's a matter of finding sigma.
Is it finding what?
To getting a high enough sigma result that they just shut up.
What's a high enough sigma result?
That means that, like, statistically anomalous. That means that's what this is. It's a signal versus a noise. That's all.
Oh, signal to noise ratio. Okay, that's cool. Yeah, I guess I'm getting that better all the time. When I started this nonsense, testing like this, we were generating somewhere in the zone of around 25 micronewtons. And we had to go into resonance just to see if we were actually making thrust. Because resonance, it jacks you up around 10x. You don't make any more impulse, but you can see a greater differential. Now I'm making 6,000 micronewtons. It's a difference, We have signal noise. This thing, this kludge that I came up with is only good to about 20 micronewtons. Maybe if you want to get technical, it's really only good to 100 micronewtons. So let's just say I'm off by plus or minus 100 micronewtons, which is the true resolution of the meter. Until you read it 250 times a second. But even if I'm off by 100 micronewtons, either way, it doesn't matter. It's in the noise still. I'm making 6,000 micronewtons. Dr. Sonny White got published making 5 micronewtons on a test rig that was only good to 5 micronewtons. And somehow, he got published. And everyone, face of warp drive. I'm not bitter. Not bitter at all.
Drew. Oh, I'll let David go. Go for it, David. David, you had something?
Oh yeah, I had. Drew, what's the maximum voltage you're applying?
Yeah, and Jared, your mic is being weird.
What the system will handle. It's not so much a matter of voltage, it's a matter of field. And I don't have it listed here, but in my notes, today's test was at 1.48 times 10 to the 8th volts per meter. To give you some sort of feel for that, air ionizes like lightning bolts. Air ionizes at around 10 to the 6th volts per meter. We operate regularly at 10 to the 8th volts per meter. So, generally speaking, it's this particular setup was like 7,500 volts. But it's really all about field. The voltage is just there to generate the field. And if you can stuff enough real charge into the plastic, then when you cut the free electron voltage, the charge is still there making the field. And it's kind of what the dream is here. Lots of places to stuff charge. But that's a dream for another day.
Is this better? Can I ask a question now? Can you hear me better?
Yeah.
Oh, good. Yeah, Drew, I had a question for you. So I'm looking at the super spiky, noisy total thrust over time, right? So I was curious on that for the different graphs that you've shown us here. It only looks noisy because of the scale that you're using, of course. But I know you said you've had trouble with trucks driving by and stinking SpaceX deciding the worst possible times to launch their dang rockets and all that other stuff that you got for the noise. But it looks like you filtered out. I was curious if not that one, the grayer one, the one that's going from bottom to top. Super noisy gray one. So it's the one going inverse to that black line. You can see it on this chart. It's the ambient force.
Oh, this one?
Yeah.
This? Yeah. Okay. I don't know. That's brand new. Okay, that ambient force graph is literally only a week old, and I don't have 100% of my programmer's time like I used to. Sadly, we have a side hustle going on, which it just shames me to even mention that I invented it, because I hate it so much. But 100% of his time is right now figuring out color for digitally controlled color-changing fingernails, of all goddamn things. So I don't have his time to fix this little problem. This should be a smooth line. It's the same exact data that's coming off the other meter at the same rate, being processed by the same code. But it's got that nonsense in it. Now, one of the other things is, this is a very small, this gray here, this gray is this scale. So see how this scale goes from 0 to whatever it is, 0.25. So this is only 250 micronewtons. Whereas this scale goes from, this black line goes from 0 to 6,500 micronewtons. So that's probably the bulk of it. Because there's only a tiny bit of drift on a meter that isn't connected to anything. It's just literally reading the thermal drift of the system. And that's only about 2 millinewtons up during the course of the day and 2 millinewtons down over the course of the night. So there's only about 4 millinewtons total throw in that particular meter. So that's where that information's coming from. This right here. I'm going to use it to show me whether the stupid meter is drifting up, holding its own, or drifting down, because that tells me what's going on with the estimated drift curve.
That's kind of where I was
hand waving going on here. So, sue me.
That's kind of where I was going. I was wondering, that downwards going black line for your actual thrust, right, up to 6,000 micronewtons. Like, yeah, that's super pretty. But like, if you were to include error bars on that, right, what it might look like with the min max kind of thing. And it seems like with that ambient force thing, you're kind of like giving yourself error bars.
Yeah, I'd say the error bars are probably plus or minus 500 micronewtons. Probably plus 500, minus 500.
So
I think that would be a
mil
fair
total?
error bar. A what?
So a millinewton total?
Yeah, I would think that'd be fair. Yeah, I think the error bars are well, actually, I don't think they're going to be any more. I'm pretty liberal. I'm pretty kind to myself when I do error bars. So it's probably minus nothing plus 1. So it'd be up here. The error bar would be we're at 6.5, so it'd be at 5.5. So the error bar would be here and there. It'd be right inside the line.
And that all ties back into what Brennan was saying about, your sigma of confidence, right? So if your error bars are really, really small and your signal is really, really strong, in this case, if you're getting 6 millinewtons and your error bar is, 0.6, then you have a sigma, you're good to 1 sigma, right?
Oh, I don't know. I still don't even.
I probably have that
understand
wrong.
what that means.
I don't know.
Sure.
No, it's higher.
But again, this runs into my fundamental philosophy is error bars and trying to convince other people that this is real is what those, well, we'll just call them the Jack S's of the world care about. I don't. I don't care if anybody believes me on this or not. I don't care if y'all believe me. I hope you do, because I'm not out to lie to you. But if every single person on this list tells me I'm wrong, I'm still going to do what I want to do. And there's still going to be more of these things getting generated next week. And they're going to be better than the ones this week. And that's what I feel. So I don't have to actually follow any of the, whatever they are, the Sigma people of the world. I mean, I'm sure there's a society of them. So God help me if I ever have to present this in a paper of some sort, because I'm not going to do it.
Yeah, that's like the upper division physics lab. They make you do that when you get a physics degree. Like they teach you how to do this stuff and all that. But a lot of theorists I talk to, I wonder if they've even taken that. So. But
an engineer to get their data, the engineer doesn't care what they're thinking.
Yeah, the thing about it is, what you have is repeatable, right? Those are the important things. It's repeatable. There's systemic errors. You can address those. I mean, it's just it's all, especially when it's repeatable. That makes it much better. And that was the challenge that we had with Jim stuff, because when it was on the ball bearings on the steel ball bearings and the steel rods, those things would scrape up the rods, and then you'd have to build a whole new one for it to get it to work, and it would work great for a few weeks, and then it'd be like junk. So repeatability is huge with any experiment.
Yeah, I'm sure it is.
And it doesn't matter sometimes, even if you have all the sigma, right? All the certainty, right? So in a slightly unrelated field, Beatriz Villarreal, who is a UFO scientist, she's a scientist that does UFO stuff. She found all these hundreds of thousands of transients, and she did all the math on them, figured out, they show up when it's not an Earth shadow, and they don't show up when it is an Earth shadow. So it's showing they are actually there. They're not defects on place. And she gets it out to 23 sigma. I think it's 22.9 sigma right? So it's more likely that like we get swallowed up by a black hole this very next second than that there's an error. And it doesn't matter. People still like immediately look at it and go, ain't no way, right?
Yeah,
So
that's
if
because
your
you don't have
results
the
are
repeatability, right? It's like, show me the thing, and we can't do that. So anyway, that might resolve itself. But yeah, you're right, Jared. Having a high confidence in statistics is not necessarily the only thing that matters.
This was the material I was going to show off last week until the last time until the meeting got hijacked by an idiot. This is titanium dioxide infused Kapton, and this is called, I don't know what this is called. It doesn't have a name. Okay, doesn't have a name. Anyhow, this is titanium dioxide infused Kapton, and it has a permeativity of around 1,000, which typical Kapton has a permeativity of around 3.5. And if you're done more and you have more money than God, then you can figure out ways to embed the aluminum onto the surface of this magical material. And then you have titanium infused Kapton with a conductive surface. I don't know how they did that. I can't make it happen. But you're way better at this than I am. And this is sold for a space program. This is the space program samples, which if you work in a space program, they're willing to send you samples. You know, more cool materials out there. Lots of coolness.
nice. David,
Drew,
you had
what-
something?
Yes, David.
Oh, Drew, what happens when you reverse the polarity of your applied voltage?
It produces thrust at around 60%.
In the reverse direction or the same direction?
Same direction.
Okay.
It has nothing to do with the polarity of the field, because our thrust is created with an E squared. If you look at our thrust formula,
Okay.
it's there's a E squared in it, so it doesn't matter which direction that the field is going in. And you would think it would be 100% both directions, but and I have absolutely no idea why this is, but the universe doesn't like positive holes. If your goal is to make thrust, the universe interacts with negative charge. We'll just call that 100%. And if it's a positive hole instead of an electron, it deals with it at around 40 to 60%.
That's very
Usually it doesn't
interesting.
short out, because these things really love to short out if they're flipped over. Positive is just not the answer for making impulse drive thrust. It just isn't.
Drew, do you have any friends in the southern hemisphere? Because it might be interesting to try testing your devices in the opposite hemisphere and doing these reversal tests as well, just to help negate any chances that there's magnetic field interactions on these electrostatic thrusters, right? So I know you've already got it shielded 15 ways from Sunday, but just for, again, that added certainty factor, I know that my thruster does 100% thrust in one direction, 60% thrust reversed in the northern hemisphere, but you do in the southern hemisphere too. And now you have, you've proved that, the magnetic fields don't matter at all.
I have friends in the southern hemisphere. But
You actually don't need to go to that extent. You could just make a magnetic field.
Well, you could Helmholtz it. You could Helmholtz it, but
we have done that. I have put a 16,000 Gauss supermagnet in there. The surface on the is that a real number, 16,000, or is that stupidly high?
That's about right. 1.6 Tesla.
Yeah, whatever. So it's 16,000. I remember that from a long time ago. We would put 16,000 Gauss magnets directly underneath the pendulum, then turn the damn thing on, and it would just, it would just do its magic. And when we had Boeing come and visit many years ago, they were stunned that we had a 16,000 Gauss magnet about 1/8 of an inch away from a thruster, and it made absolutely no difference. And we produce thrust this way, and then we'd rotate the thing 90 degrees and produce thrust that way. 90 degrees and produce thrust that way. It didn't matter which way you turned it. That was a lot of fun.
One other question for you, Drew. So the Van Allen belts there, they got all sorts of stuff going on up there, right? You got your X-rays and your charged particles, and there's a bunch of stuff flying around in them radiation belts. Is there any way that you can try to mimic, other than vacuum, any of the stuff going on there?
Yeah, I could just lower the vacuum and have a lot of plasma in there. I could fill the chamber with plasma.
I'm just thinking stress testing. You've already proven it does the thing. Now prove it can do the thing in the worst possible place.
Well, that's what flying in the space would do. We would have to go into the real space in order to simulate all of the mischief that's up there in real space. You got hyper ionized oxygen with a triply ionized oxygen moving at 17,000 miles an hour, smacking into the thing, causing all kinds of mischief. And that's our goal. That's our dream. Our dream is to put it all together and stick it into a little satellite and throw it up into vacuum and see what happens. Hopefully, about a month from now, maybe a little more, maybe 6 weeks from now, we'll be a whole lot closer to that happening.
I wanted to couple on what Jared said really quick about Villarreal and the plates, and actually, it's that sigma. By the way, each time you repeat it, the number goes up, right? But that number is probably even higher because there's this guy Donald Menzel who was in charge of the astronomy department at Harvard right then, who is notoriously destroyed a lot of the glass plates that are the primary source of what Beatrice was working with. So like the fact that she found anything is actually kind of a miracle because she's working uphill against, of all the people that would know what it means to destroy that kind of repetition, it's this guy. It almost seems deliberate, but it happens to be the case that he's was a notorious UFO skeptic out there in the world publicly at the time.
And
that was
he had CIA connections, and he was big on debunking the 1952. If anybody wants to go down a rabbit hole,
bingo card just lit up, like all of the boxes just got checked.
Look up the Menzel gap. The Menzel gap. That's where he said, we don't need these plates anymore. We don't care about data that we haven't looked at yet. We need more space.
Anybody that defends primary source destruction, just stop listening to them immediately. Like that's just an off switch. Sorry.
He knew what he was doing. And even the students, the grad students that he had hired to clean out this giant, 40,000 square foot room full of these plates of stars, 40-minute exposure times on 5x5 photographic plates. He told all these students to just start throwing this stuff in the garbage, and the students were so horrified that they were dumpster diving and they were saving them. And so that's why we have 1/3 of the plates. I think he either got rid of 1/3 or 1/3 remained. Either way, a good chunk of that remains came from students that took it out to the trash, and the other students went into the trash, said and saved them.
Similar, but parallel kind of story as Tesla's chests. Reminds me of that.
Well, here's another piece of impossible. That's depressing. About 40 years ago, when I was a young college pup, worked with the crazies over at Rosemary Hill, which is the University of Florida's astronomy division. And they did glass plates back then. And the only reason I cared about it was that they were building vacuum chambers to hyper gas sensitize the glass plates, which were basically X-ray film, X-ray emulsion. And we would go from ASA 1 to ASA 2 million. And they would put the glass plates on the telescope and they open the shutter and take pictures, and they were doing quasar research or some nonsense. But one night, they get all done, they're developing, I just happen to hang with them once in a while. And the guy shows me a plate. I'm like, woo, check out the plate. That's cool. You got little stars, you got galaxies, and what's that? What's that thing doing? Is that a bug? Did a bug crawl on your freaking plate? He goes, no, we don't know what that is. Whatever it is, it changed direction a couple of times over the 6 minutes this plate was exposed. I'm like, well, it wasn't anything I did, guys. And they're like, no, it wasn't anything you did. And we don't even think it was inside the telescope. We think it was out in space somewhere. Like, really? Okay. Can I have that? I'm like, no, you cannot have that. So, I don't know. Those guys hit it. They did 20 plates a night for fucking years. Years and years and years. So, there's a whole lot of glass plates out there. And one or two of them got to have something interesting on them.
Definitely. So maybe to give you guys just a little update from Europe before I drop out, because it's getting a little bit late here. So first of all, I wanted to say, Curtis, man, I know you have a lot on your plate right now, but your paper, I'm so looking forward to seeing that, because I think this is the really important part, right? We have to have theory and experiment come together. And to do a really good experiment, you need to have some knowledge about the theoretical background. So I think that the stuff you're working on is definitely going to help us a lot. And I also think that the stuff that Jack Sarfatti is working on can help us a lot. So I was also very pleased with the whole conference today. It was a very good conference, I think. And Tim, you did an awesome job, even though you're
Thank
a
you.
little ill. Like
Yeah.
seriously, I know that it was a little bit difficult today with the schedule changes and everything, but I think it was a great conference, and I enjoyed it very much. And I think we can get a lot out of the sessions which will come out of the conferences more, right? So
yeah. Well, and I'm really pleased, and I'm pleased that we were able to, share some nice things about Jim as well. And let me apologize for being a little disorganized today. Sometimes it goes really smoothly, and today it was just like I had a bunch of schedule changes and the flu on top of it. I'm just like, oh,
yeah,
okay, but
totally fine. And so, like, we're actually going to try to apply for a grant by ESA. So we're going to see if it's going to be the same nightmare as NASA for you guys. So far, it's a lot of bureaucracy, and it's a very slow process, but we're going to see. And I can say that from the Heim theory work group, there's more and more activity going on. There has now been one meeting for the discussion of experiments, and this is going to be an ongoing setting. And we're trying to bring this to APEC as soon as possible in a very good setting. I could already maybe give now a presentation about what has been done historically, or what the ideas historically have been, but I want to do it in a really good informed way, and maybe have a modern proposal of the experiments. So it's going to take some time, but it's in the works. And yeah, some more people are getting also active in the group, which is a very good sign. And I think especially what you said, Tim, the worldwide connection to the internet, the pace of the information space, the way that we have the possibility to work together globally as human beings towards a common goal, right? This is something very strong, powerful, and can be really impactful. And I think we're doing quite good in that regard here. And yeah, I just love to continue this. And so I'm going to go to bed now, but I'm going to be seeing you guys probably in some days with Jack Sarfatti, and in some weeks at Open Mic, and so on and so on. So have a great session, continue on, and see you soon.
Okay. Well, thanks again, Joel. Get some good rest, sir.
Bye.
Tim, I think I'm going to take the same route.
Well, guys, why don't we close things down for today then? If
I have a quick question for Drew.
Yeah, go for it, David.
Drew, I'm fascinated by your E-squared dependence. Do you have a preliminary write-up that would be available?
Yeah, I got 78 pages of patent. Go look my name up on the patents, and anything you see with the words Charles Bueller attached is this. And like I said, contact me offline, and we'll have a really good discussion on it.
Okay. I watched your YouTube on how to build the thruster.
The whole formula's out. You what now?
I watched your YouTube on how to build a thruster. Thanks for doing that. That was great.
You're welcome. Curiously enough, the patent office said, no, that doesn't count. But we showed people how to do it. Straight from the patent. told them to go read the patent. They did it. They sent us videos of them doing it, them working, but none of that counts. Oh, no, that doesn't count. Oh, that's curious. No, anyhow, yeah, give me. I don't know how you're gonna get a hold of me. You got my email or anything? I'm not putting it out online, but you got my email. Tim,
You can put it in the private chat.
The private, okay.
Yeah. Yeah, and then
if not, I can connect you, David, with Drew. I got both your emails.
in just a moment here, why don't we close things down for today? I'm starting to fade too. I've been kind of flat on my back for the last couple of days.
It's only 6 o'clock.
Yeah, I know.
Yeah, maybe where you live. Okay. It's in the chat. Obviously, fix the thing that ain't what it should be.
Yeah.
And again, I really look forward to Curtis's paper. I won't understand a word of it, but hell, I can read it. And Jared, another session went by. No Graphic Flyer updates.
I cleaned it up. You see, there is no more Graphic Flyer because
I see nothing. No more Graphic Flyer.
Yeah. You could replicate Eric's experiment, Jared. That'd be a good idea. Somebody's got to do it.
Yeah.
Gentlemen, it's been fun.
Thanks again. Okay, well, why don't I close things down for today? This has been APEC for Saturday, August 30th, 2025. Signing off, everybody. And I believe our next one is September 27th, if I remember correctly. And then it's October 18th after that. So